All right, well, why don't we get started? Welcome everyone to what it looks like a very beautiful Pi Day. The first great weather in a while, and we're going to be indoors for 24 hours nonstop. So, Van, yeah, what's up?
You said your camera's off.
The camera's off. Oh, yeah, I better put the camera on. Thanks, Van. Let's go with that. How's that look? Thanks. Yeah. Hey, everybody. Welcome to Pi Day. So we're going to get started in a minute. I'm going to give you guys an introduction to the introduction to discrete math. But before I do anything, I want to introduce the four of us that are doing this. I'm Cory Palmer. I'm a professor in the math department at University of Montana. And why don't the three of you guys come up here and show your faces on camera? Let's introduce in order of appearance. So this is Ryan Wood, a PhD student in the math department here. You'll see him in about 3 hours from now.
Yes, I'll be back.
And then next up will be Van Magnan. Say hi, Van.
Hello.
Van will talk to us in about 6 hours from now. And last but not least, Anna Halfpap, who will be talking to us in, I think, 12 hours from now?
Oh, more than that. I
More
started
than
at
that.
4 a.m.
At 4 a.m., yes. So make sure you come and support Anna, 4 a.m. That is heroic. All right. Excellent. Thanks very much, you guys. Okay, so let's get started. I want to give an introduction to discrete math. And first, I will describe what the subject is all about, and then we'll actually solve some problems. And there's a very high percentage of math PhDs in the audience and in the chat, so forgive me if some of this is elementary, but I think it still should be enjoyable. And not everyone is a mathematician, of course. Okay, so let's switch over to a full-size slide and start talking about what is discrete math. Okay. So discrete math is the study of discrete structures. Right? But what are discrete structures? Well, they're things like the integers, so those are accounting numbers, 1, 2, 3, 4, 5, 0, and the negative numbers. Sets, so just collections of objects, like all the people in the audience here, or all the people in the Twitch chat, or all dogs that have 3 legs, right? Those are just different sets of objects. And networks. So what are networks? They're things like a social network, for instance, is a discrete structure, or a transportation network. Okay? And that's something we'll hear about much, much later, maybe starting at 4 a.m. about networks. And here the word discrete means like separated from one another, as opposed to continuous. Sometimes we classify mathematics into discrete and continuous. There are other ways to do it. Many of you are familiar with calculus. That's a typical continuous subject. Discrete is sort of the other side of the coin there. Although there are nice crossovers, and we might see a little bit of them here as well. Okay? All right. So one important thing, and one reason discrete math has become so popular, is it has important connections to computer science and probability, and many other subjects, but especially the rise of computer science has been highly relevant to the importance of discrete math. Computers have data structures that themselves are discrete structures, and computer programs are discrete structures. Okay, so those are things we study. Right. There's this quote, I'm paraphrasing from Miklos Bona, and he has a textbook about combinatorics, which is a part of discrete math. This is my favorite part of the subject, and this is true in other parts of mathematics as well, but what we often discover in discrete math is that very, very simple tools can be very powerful, and on the other side, very elementary looking problems can be incredibly difficult and unexpectedly deep, and often open, unsolved. Okay? And we may see a couple of those as well. Last couple here. So the big topics we're going to go through, for the most part, can be maybe fall into these 3 broad categories. Counting, enumeration. This is one of the oldest human activities, and we'll be doing some of it here. I love counting. My students do as well. Recursion, which is, well, I'll let Van tell you what recursion is when we get there. And graph theory, which is the study of networks. Okay, so these will be sort of our big 3 topics. And then to characterize how we're going to talk about things is, discrete math is especially characterized by problems, individual problems that we solve, and there's a sort of theory or methodology that grows out of those problems. And again, I don't claim that's unique to this subject, it's just a way it's been characterized very much. And that will be our approach here as well. We'll be doing individual problems, and the theory will come out of those individual problems. The problem format is also, I think, appropriate for this format of presentation. Okay? So with that in mind, let me state 4 very interesting problems that we won't solve yet, but we'll see solutions of them as we get further along. Okay? So the first and incredibly common, and many people have thought about this before, of course, is what's the probability of winning a lottery? Well, we can answer this with discrete math and with counting. That's something that we'll definitely do later on. Ryan will talk to us about that. You can also just count objects, right? How many triangles are in this cool Rubik's-like thing called the pyraminx? It is a neat name there. That's not too hard to sit down and figure out how many triangles are in that picture there. You can ask further questions, though. What if this had larger dimensions or was just bigger and had more triangles in the face? Could you come up with a general formula? Here's a classic. So suppose you're at a party and you're interested in how many people at a party guarantees that you'll have a group of 4 people who all know each other or 4 people who all don't know each other. Can you make a big enough party to guarantee that this will happen? This is closely related to graph theory, and Anna will talk to us about this. Okay, and this quickly leads to a very famous open problem. Okay. We can do cool equalities like this. Look how pretty that is. The sum of the first n cubes, and then you take its square root, and you get n times n plus 1 over 2. That's cool. We can prove that. Right? Those are very neat. And actually, maybe I'll take a moment to talk about why we even care about something like this, right? So this is where the connection to computer science is particularly profound. Imagine in this inequality here, or this equality here, that you wanted to compute the left-hand side. For some reason, you needed to know the sum of the cubes and then their square root. Right? Well, you can easily write a program to take 1 and cube it, add the cube of 2 to it, add the cube of 3 to it, and so on and so forth, and then take the square root. That's not that hard. Your calculator can do it very quickly. But if you know this formula, you can compute it much, much faster. Right? You can just multiply n times n plus 1 and divide by 2, and this computation is done much quicker. And, well, speed for computing is, of course, very valuable to us. Even with the rise of very powerful computers, the faster you can do computations, the better for many applications. Discrete math is abundant with things of this nature, more complicated than this as well. Okay. And then finally, let me just wow you with what looks like a really cool formula. This is something I love very much. You may not recognize these symbols, but you will if you stick with us long enough. So we'll prove things like that. Okay, so let's jump into some actual problems. All right. Okay, so first problem, very, very, very simple. Right? The game of Twister. I hope many of you here are familiar with Twister. You spin that wheel, and wherever it lands tells you where to put a foot or a hand or something like this. Okay? And so my question to you is, if I spin this thing, how many outcomes are there? Anyone here care to answer? I know it's not that hard, but Anna?
16.
16. And why is it 16? Did you count up all 16 squares?
I multiplied 4 times 4.
You multiplied 4 times 4, exactly, right? If you multiply 4 times 4, you see the way that this thing is arranged, right? There are 4 categories for each hand and each foot. So 4 total categories, and each have 4 colors, so you just multiply the 2 together. Okay, so that's already a very simple shortcut to counting. Instead of individually enumerating all 16, we can see that it can be answered as 4 times 4. Actually, there's other ways to do it here as well. You might notice that, oh, there's 2 hands and 2 feet, so you might split it into hands and to feet, into 2 categories. And then for the feet, there's 8 outcomes, and for the hands, there's 8 outcomes. So 2 times 8 would also give a solution here. Okay? So very, very simple counting problem. But this leads to a more general rule that we're going to spend a bunch of time doing in the first part of the lecture here. Okay? All right. So I want to state something called the product principle. And what I want to make clear is that this product principle is something that you already were taught in elementary school and are probably very comfortable with and sort of understand implicitly. But like I promised you, like Miklos Bona promised us, simple tools can lead to unexpected results. Okay, and we'll see some with this as we go on. Okay. All right, so all this says is that suppose you're doing some sort of procedure and it takes 2 steps. And in step 1, there are A ways to perform the step, and in step 2, there are B ways to perform the step. Then of course, in total, there will be A times B ways to perform the operation. Right? Just like in the previous example with Twister. There are 4 ways to choose a left or a right hand, left or right foot, and then for each of those, there are 4 different color outcomes on the spinner there. So this says, oh, the answer to the spinner question should indeed be 16. Okay? This product principle can be generalized easy. If you have a procedure that has a 3rd step, C, right? After the first 2 steps, what would you imagine is the number of ways to solve a problem? And let's actually go to the whiteboard. This is simple, but we should use the whiteboard a little bit here. Let's see, I think I've got the whiteboard visible now. So suppose we had 3 different steps. So step 1, in A ways. Step 2, in B ways, and step 3 in C ways. Okay? I'll ask the audience again, if that's the case, how many ways do you think you can solve the problem? Multiplication, right? Multiply A times B times C, all right? That's the total number of ways. And I mean, I could just tell you that that's true, but actually, if you'll notice, we're using the product principle in disguise here, right? How many ways can I perform step 1 and step 2 together? A, B ways, all right? And then if that's my new sort of step 1 prime, I can combine that with C, my second step now, or my third step originally, to solve the problem in A times B times C ways. And we can actually generalize this for as many steps as we want, and we'll see that later as a solution to one of our problems, okay? All right, anyway, so let's jump forward here, and I want to ask a cool question here, again about Twister. Let me get it set up correctly here. Okay, so we had Twister question number 1, and here's Twister question number 2, right? So in this image on the right here, or on the left, I guess, that's the patent application for the game of Twister. From 1969 was when it was granted. The question I'm asking you here is, how many circles are on this Twister mat, right? And again, we can sit down and count all of them, but we can also use the product principle here, right? If I can describe all these circles by 2 properties, right? A step A and a step B, right? Step A might be choose a row. There are 6 rows. And then step B is choose a column. There are 4 columns, so 6 times 4 total squares, right? Circles, 6 times 4 total circles. Each circle is characterized by its row or column position. Okay? Unsolvable. Okay, thanks. Yeah, all right. No, it's a question of the video quality is not going great, so, okay. So one thing I want to read to, just because I think this is quite amusing, is, like I said, this is a patent application for Twister, and on the application it says, this is an apparatus for playing a game wherein the players constitute the game pieces. This doesn't have anything to do with the solution, but I think it's pretty charming. So anyway, so let's actually answer the question here, right? So we again have our 2 steps, A and B. Right? I'll switch over to the big screen here. And A is, well, in this case, equal to 6 rows, and B is equal to 4 columns. And so the total number of squares, I don't know why I keep saying squares, it's circles, but the total number of circles is 24, right? More importantly, it's 6 times 8. 6 times 4, 6 times 4, yeah. Sometimes it's tough to do arithmetic at the whiteboard, so. Yeah, indeed. So that's a use of our product principle there. And again, like I was saying, this is a shortcut, right? Instead of counting them all up, we have this procedure for breaking it down into a simpler method. And I want to do a few more of this type. All right. Nice. Okay. So, yeah, all right. So a typical variation of this type of problem, now we'll have 3 steps, is suppose I'm building an outfit out of my wardrobe. This is not too far off from the truth here. Suppose I have 4 shirts, 5 pairs of shorts, and 3 pairs of shoes. That part's not true. I have 1 pair of shoes. How many different outfits can I make out of this? Well, again, we can use our product principle that is actually articulated already right here on the board. So let me switch over. Okay. And in this case, how many different options do we have for A, B, and C? Well, for A, we have 4 different shirts. For B, so I'll say shirts, 5 different pairs of shorts, and 3 different pairs of shoes. Whoops. Okay. And as we promised, all we need to do is just multiply these 3 quantities together to figure out the total number of outfits. Right? So if we multiply these A times B times C, then we get 4 times 5 times 3, which I think is 60. Is that right? Probably. I have them written down just in case. I can't compute on camera. So. Yeah. One thing I want to highlight here, again, is that the product principle is really versatile here. So we did just use a generalization of it where I just said A times B times C. But the procedure of building my outfit can be broken down in different parts, right? The way I tend to dress myself before I leave the house is maybe choose my shirt and my shorts in my room in one step, right? That's my first step. This could be thought of as a step A, right? And this can be thought of as a step B. I choose my shoes just before I'm about to leave the house. And so you could solve the problem this way instead. you can say, just like here, A times B is the number of options for the first step. Well, in that case, there's 20 options by actually literally applying the product principle to just these two. And then there are 3 options after I've chosen my clothes to choose the shoes. And so in total for these two, I also get 60. And of course, you can arrange it in any way you want. In fact, you might even ask, in how many ways can you dress yourself with these pieces of clothing? And that's another question that'll get answered later on. All right, so that was pretty easy. Let's do one that's a little bit harder, or will be after a variation of it. And that's this here. So I would like to create sandwiches out of a certain number of food materials. Let me erase here. Okay. All right. So here, what do I have? I make a sandwich and I have bread, meat, vegetable, fruit, and cheese, right? Okay. And again, I hope you see that this is just a variation on a theme. Again, we're using the product principle with, I think, 5 steps now. All we need to do is articulate how many are in each of these categories. Let's just label them A, B, C, D, and E. So breads, I think there are 4 types of bread, if I remember correctly. 5 types of meat, 2 vegetables, 2 fruits, and 3 cheeses. What would the product principle tell us to do? How do we solve the number of sandwiches we can make here? What do we have to do? Multiply everything, exactly. We just have to multiply all these quantities. Okay, so number of sandwiches equals 4 times 5 times 2 times 2 times 3, which, and this is embarrassing, but it's 240. The math counts kids I work with would be embarrassed for me. They would solve this in an instant. So that one's easy enough. Now I'd like to make a wrinkle on this problem and introduce sort of a really nice technique that we often use in mathematics, and that's pretend. Okay, so let me explain what I mean by pretend here. Oh, I see, the whiteboard wasn't so good there. Okay, so now I want to modify the question slightly here, right? There's always talk about what makes a sandwich. For me, in this case, a sandwich will be made of you need bread. Everything else is optional. As long as you have bread, you have a sandwich, even if there's nothing between the bread. Okay, so now my question is, the minimum sandwich has bread, but it might not have meat, it might not have fruit, it might have cheese, but it might not, so on and so forth. How does this problem get modified? Well, you can try and figure out, okay, well, what about how many sandwiches don't have meat? How many don't have fruit? How many don't have cheese? And so on and so forth. And you might end up in some sort of like inclusion-exclusion, which we'll learn about later. But there's this cool pretending trick, and that is, let's just think of no meat as its own meat. That's not really a meat, right? The empty meat, let's call it here, right? Okay. If we do that, then we can build a sandwich in a very similar fashion, right? So now in the meat category, oops, let's say meat, right? We have, I don't remember what the kinds are, but it's worth listing here the first time, I think. Chicken, turkey, ham, bacon, salami, and none. We can just pretend none is a type of meat, right? That's something that can be selected and put on our sandwich. Okay? Well, in this case, now we have 6 different types of meat, and we'll have now 3 different types of vegetable, right? The non-vegetable as well, the choice selection of no vegetable. 3 different types of fruit, and I think it becomes 4 different types of cheese. Is that right? There were 3, and then we get 1 more non-cheese. And now we can just do the product principle with these things here, right? That's the number of sandwiches, and this will account for sandwiches that don't include certain materials here. In fact, what would the all-bread sandwich look like? Well, it would look like a choice of bread from 4 options, no meat, no vegetables, no fruit, no cheese. That would be 1 specific option from each of these categories. And so now, the number of sandwiches equals 4 times 6 times 3 times 3 times 4. I think this was 864? Maybe someone can do that very quick. That's a trickier one. 864 is what I wrote down. So more. Of course there should be more, right? There should be quite a bit more. Okay. Does that look right? It's not important that be confirmed. What's that?
It's much more.
It's much more. It's much more. Yes, indeed. All right. Okay, great. So let's jump to another one here, and keep in this pretending idea. This will be really handy. This is a really common strategy we use. Okay. So this question is, I mentioned math counts, this is directly from math counts. If you are past 6th grade, you should be able to solve this. It's not as easy as it looks, okay? So we have the following question here, that Dak has 4 different coins. He's got a quarter, a dime, a nickel, and a penny. And I would like to know how many different amounts of money can he use, can create by using one or more of the coins in this collection. Okay? So, one option again is to start listing them. Well, you could take a quarter and a dime, right? That's 35 cents. You could take a quarter and a nickel, that's 30 cents. You could take a nickel and a penny, that's 6 cents, and so on and so forth, but that's not the way forward here, right? The whole idea here is being clever and being tricky and answering these questions in a faster manner. So let's think about the product principle again. So the product principle breaks problems down into step A, step B, step C, and so on, okay, if you can. So if I was actually building up an amount of money using these coins, I could build it in the following way. I could make a decision for each coin, whether I take that coin or not, right? Just like we did with the sandwich, right? We decided whether or not we wanted which bread we wanted, then which meat we wanted, and so on and so forth. Here we just decide whether or not to take a quarter, okay? Well, we only have 1 quarter, so we either have the quarter or we don't have the quarter. And one thing to note, I hope everyone recognizes that whether or not you take the quarter is an important decision here, right? If I take the quarter, whatever money I build with the rest will never be the same as if I didn't take the quarter, right? The monetary units are far enough from one another that you can't build them in multiple ways. That would make the question quite harder, right? Imagine we had several dimes and several nickels and several quarters. That's very challenging by comparison, and we may do that later. But in this case, well, let's think about it. We've got quarters, we've got dimes, well, dime, nickel, and penny, right? And with the quarters, we can either take the quarter or not. How many choices do we have in this first step, as far as the product principle is concerned? 2. Yeah, 2, perfect. 2 quarter options, then 2 times 2 dime options, times 2 nickel options, times 2 penny options, right? And so there's 16 different ways of putting those coins together, except I made a mistake here, right? Anybody see the error I made? That's not quite the answer, right?
Have to use 1 or more.
Yes, the question specifies that we need to use 1 or more coins in the collection. And I want to think about this for a minute. One of the outcomes of this procedure here is to choose no quarter, no dime, no nickel, no penny, right? That is one option, one of the 16 outcomes. But we don't allow that by the way the problem's worded. We said we need to select at least 1 coin. Now, one thing you could say, oh, okay, well that's tricky to do directly, but the trick here is just to subtract that off at the end, right? So there's 16 total, but one way is to make 0 cents, right? i.e. take no coins. But DAX takes at least 1 coin, so we need to throw away that option. So this actual solution, I'll just write it like this, is 15, right? Which is, well, 16 minus the 1 bad one, okay? This method of computing a larger answer and then subtracting off to find the actual solution is a technique that will be talked about later on. It's a very powerful method of approaching problems like this. This is a baby version, right? Okay. Now, what do we got next here? Ah, yes, very good. Candy. I'll be eating a lot of candy today to stay awake here, and so I thought we'd have a nice theme here talking about candy. And this will also lead into something very interesting about discrete math that I'll tell you in a moment. Okay, so one of my favorite all-time candies are Mentos, and they come in a pack of 14 candies, and there's 3 different flavors. Well, the fruit type has 3 different flavors. There's mint, there's other flavor packs you can buy. And the shape of the candies, it's not important, but they're oblate spheroids. So now you know what an oblate spheroid is from the question here, if you know what Mentos look like. It's a smushed sphere, right? So they come in a roll of 14, and there's 3 flavors. And let's imagine that I'm eating Mentos by popping them off the top, like in the commercial, right? Pop one off the top, eat it, pop one off the top, eat it, and so on. I'm curious, how many different rolls are possible in this way, okay? So we're sort of supposing there's a left and a right side. If you talk about orientations, it gets a little trickier. But let's use the product principle here to answer this. How many different options are there for this first step of this problem? How many different candies can I get when I eat the first one? 3. It says 3, yeah. So the first one, there are 3 different candies I could get, flavors, right? And then for the second one, there's 3 more. So if a Mentos pack just included 2 candies, there'd be 9 different ways to eat them. You could have, actually I don't remember the flavor names, strawberry strawberry, strawberry lemon, lemon strawberry, strawberry peach, and so on and so forth. There'd be 9 of those, you could list them all out in order. But a pack has 14, so the third, the fourth, the fifth, I'm not gonna write down 14 threes, but there are 14 threes here, right? So this is the first. Mento, what's plural, what's singular of Mentos? Anybody know? I'm gonna say that they're the same, I have no idea. So that's the first
Like
Mentos.
fish.
Like fish.
1 Mentos, 2 Mentos.
Second Mentos, I'm not gonna write down 14 here, dot, 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 14th Mentos. Maybe I should have put oblate spheroid instead there, okay. So of course we have a shorthand for this. The dot, dot, dot notation in mathematics is very convenient, but it can be ambiguous. Here it's not clear there are 14 in this list here, but the solution to the problem indeed is 3 raised to the 14th. That's our shorthand there. So there's 3 to the 14th different packs of Mentos, and I computed that earlier. That is like 4.7, maybe closer to 4.8 billion. Okay, which is, I think, amusing, right? This is something I love about discrete math and about combinatorics. Sorry, million. Just million, it's not that big, yeah. There are tricks for seeing how the reasonable, for estimating here. Well, okay, I won't go into details here, but you can pretend that 3 is a 9, and then you have 9 to the 7th, and it'd be like, oh, okay, that's like close-ish to millions, right, having the appropriate number of digits. But what the important takeaway here for me is that there's a lot, right? This little simple pack of Mentos, this very, very, ordinary everyday thing, already has an abundance of different options with just 3 types of candies and 14 in a pack. You can have 4.8 million different packs. Okay, in fact, this almost certainly means, we'll return to this many times, you probably never had, assuming the packs are randomly distributed, you've almost certainly never had 2 packs with the same distribution, unless you really, really, really like Mentos. It's pretty unlikely. Okay. Yes, good. All right, so let's continue on the candy theme and talk about Smarties. Okay. Another candy, similarly packaged to Mentos. They come in a roll of 15. Their shapes are biconcave lenses. I learned this is a thing. It's exactly what you think it is. Now you know what it is as well if you have seen Smarties. And there are 6 flavors of those. Okay, and so we don't need to do too much work to answer this one because we're going to have 6s here instead of 3s, right? The first candy in 6 ways, the second candy in 6 ways, and so on and so forth. So in total, we're going to get number of Smarties, i.e. Smarties, say packs, equals 6 to the 15. Okay. So there's 6 to the 15 different packs. And now we're getting somewhere. This is quite a bit larger than 4.8 million for multiple reasons, right? The exponent is larger and the base is twice as large. This is about 470 billion. Okay, there's a lot more Smarties than Mentos. And we'll start to understand a little bit better, the behavior of things like this. Why is this one bigger than this? Well, it's evident that it'll be bigger, because all the numbers there are bigger, but why is it so much bigger? It's quite a bit larger. A follow-up question here, that's sort of fun. I read that 2.5 billion rolls of Smarties are created each year, which is sort of an astonishing amount, if you think about it. But there's a factory in New Jersey that makes 1 billion of them a year, and in total over the world, 2.5 billion are made. If there's 470 billion of them, and make 2.5 billion of them a year, a simple question is, well, how long would it take to manufacture to literally see every single pack? Presumably, they're somewhat random when they're created in the factory. But what do you have to do to solve this? This isn't even really discrete math, right? This is elementary stuff. What do you have to do to solve that one?
Divide.
Just divide, yes, exactly. So you need to take 470 billion and divide it by 2.5 billion. And you can already see that this is going to be a large number. Yeah, it's a little bit more than 180 years. So I'll just write like this. Well, don't need the equality. So more than 180 years. So even less likely you've ever eaten the same pack of Smarties twice, right? There's a lot more of them. Okay. All right. So, okay, on to some really neat stuff. These are very natural questions that arise in our daily lives, is counting things, especially numbers, that we interact with all the time. So I want to talk about Social Security numbers, okay? So Social Security numbers come in this format here. There's 3 numbers, then 2 numbers, then 4 numbers. And historically, these 3 categories had some meaning to them. There was a time when the area number corresponded roughly to where you were born in the United States. The group number was some subcategory of that, and then the serial number was sort of like unique to individuals in that group. Nowadays, though, they're more or less random, right? If you'll notice, with restrictions like that, you run out of too many Social Security numbers. In fact, a quick question here, that's a warm-up before we answer the full question, is, given this model, how many Social Security numbers are there with just this thing here? Let's look at that. This is a product principle as well, but now we're not really doing, we're not counting real-world objects, so we're just counting a string of numbers here. Right? So there are, I believe, 9 digits there, right? Yes, there are 9 digits here, 3, 2, and 4. And each of the digits, for the moment, can take on any value 0 up to 9. Right? So for the very first digit of a Social Security number, there are 10 options. And for the second, there are 10 options, and so on and so forth. So there's 10 to the 9 total options, right? Ranging from all 0s to all 9s. Okay? So this is a billion. Okay. Which is already a little bit uncomfortable. Are there 400 million Americans now? I think maybe we're close to or around 400 million. And not just Americans have Social Security numbers. Green card holders and so on can have Social Security numbers. And so you might imagine, and everyone who, since Social Security numbers have existed, had a Social Security number as well. So you might feel like, well, we might be approaching 1 billion, or eventually we're going to approach 1 billion. So fortunately, some are recycled. What I'm trying to get at here, though, is that we have to get rid of the area numbers. Like if we restrict the first 3 to some smaller space, we're not going to have a billion. Okay? All right. Now, I want to answer this question in another way here, just again to show the versatility of the product principle. So here we answered it digit by digit. Each digit had 10 options, and there were 9 digits. So 10 to the 9th. But you can also break it up into 3 subproblems. The area numbers times the group numbers times the serial numbers. Obviously, you're going to get the same answer, but let's go through that real quick here. So how many area numbers are there? How many group numbers? And how many serial numbers? Okay. So you have these categories here. Well, each of these problems can be addressed with the product principle themselves, right? How many area numbers? 10 times 10 times 10. Or you could just say, oh, it ranges from 000 to 999, there's 1,000 of them. You can do it directly like that as well. Okay? So area numbers, there's 10 to the 3. Group numbers, there'll be 10 to the 2. And serial numbers, there's 10 to the 4. Okay? And then putting all these together with the product principle, you just multiply this times this times this. So I've broken into different subproblems. 10 cubed times 10 squared times 10 to the 4th. And if you remember your exponent rules, and I know that you do, exponents add when the bases are the same. You get 10 to the 9th here, which you should. That was our solution here. Just another way to solve the problem. Okay? Let me add a little bit more here to the problem, because we can actually answer the true question. And there's some interesting information here about it as well. So like I said, today the 9 digits are essentially random. Anything's available, but there are a few combinations that are not allowed. This may be interesting to you. Area number 000, 666, and all the numbers 900 to 999 are not allowed for area numbers. Okay? I don't know why exactly. Well, I have some guesses for some of them, but in general, I don't know why those are the restrictions. Group number 00 is not allowed, nor is serial number 0000. 4 zeros is not allowed. Okay, so these are all the not allowed things. So we can answer this question now, but notice if we want to answer this problem, we cannot go digit by digit anymore. Right? How many area numbers are there? Well, it can start with a 6 and then have another 6. It just can't have a third 6. And so you'd have to figure out, well, how many start with a 6 but don't end with have 2 6s after? Well, there's one of those, but there's it's hard to break it down that way. Instead, let's keep this model. Figure out the area numbers, figure out the group numbers, figure out the serial numbers, multiply the 3 solutions there. Okay? And this isn't that hard, of course, but let's try. Okay, let's start with the easy ones first. So the group number, 00 is forbidden. Well, that's only one number forbidden out of the full list there. So the total number of group numbers is, well, we can say 10 squared minus 1, or we can immediately just observe that there's 99 of them. In fact, a common mistake would have been to guess that there were 99 group numbers initially, not 100. It's very common to forget to count 0, 0, but here we shouldn't, okay? So there's 99 group numbers. Serial numbers would be very similar as well. Only one of them is not allowed, and so there are 9999 of them, or 10,000 minus 1. I'll maybe write this one in reverse. 10 to the 4 minus 1. Right? The area numbers are trickier. So we're certainly going to start out with 10 to the third total of them, and we just have to subtract off how many there are. And it's easy to make an off by 1 error here. But 0's out, 666 is out, that's 2. How many numbers are there in the range 900 to 999? Be careful. Yeah, there's 100. There's not 999, there's 100 of them. So in total we lose 102. Right? 102 are lost here. Okay, so 1,000 minus, so that's what, 898, I think. Right? And so the total number actually of Social Security numbers will be 898 times 99 times 9,999. What's this going to be very, very roughly? Yeah, well, a billion roughly was what we started with here, but here it'll drop like actually by a full billion, full million, right? We'll only get up to about 900 million here, right? This is below but close to 900, and these ones are pretty close to the corresponding 10 and 10,000. So this is like, it's less than 9 billion, sorry, less than, what am I trying to say here?
900.
Thank you, 900 million. Yeah, thanks. So this slight restriction on the leading numbers dropped us by about 100 million, but maybe 900 million still is enough. They do get recycled. Numbers get reused eventually, okay? All right. So now, we talked about Social Security numbers. Let's talk about credit card numbers, okay? These are also historically very interesting, and I will also teach you a cool algorithm related to these, which I will do with this. This is a fake number, although it is a valid number. I mean, it's not an actual one, but I will explain to you what valid means here, and I'll break down what's going on with credit card numbers, okay? All right, so credit card numbers, well, there are many different types, not all over 16 characters, but we'll look at these of this type that have 16 digits in them. And I want to break down the meaning of each of the pieces here, okay? So the first digit is what's called an industry ID, and numbers 1 through 9 are used for those. They often correspond to the big issuers. I think a 4 is Visa, and maybe 5 is MasterCard, and so on and so forth, okay? But there are other specialty ones there. But you don't have control over that number, it's not random, it corresponds to your issuer. Or the processor, maybe it's called. The next, what are these, 5 digits, are the issuer ID, okay? So each, MasterCard has thousands of different cards issued by tons of different banks, like your Bank of America has a bunch, and they have different rewards cards. Each of those has a different issuer ID. For the sake of this problem, I tried to discover how many issuer IDs there are. It's not easy to figure that information. It's sort of, the American Banking Association issues them out, and you can send an email requesting them, but you need like special authorization. You need a reason to be able to get these. You may see some reason why these are hidden, okay? But those also are not random. They correspond, right? If say, me and Matt have the same card issued from the same bank, our initial 6 characters, the industry and the issuer ID, are going to be the same. But we will have different account numbers, okay? So the account number, that corresponds to an individual. Those are unique per individual on that specific issuer, okay? There's only a billion of those though, right? You see there's 9 digits there in the account number. We've already answered that question a minute ago, that there's a billion of those in each individual issuer. And then there's the 16th digit, and I denoted that as a checksum. And I'll explain exactly what that is and how it's computed, but the point is, that's not random. That is determined by the previous 15 explicitly, okay? So what this means is that on a specific network, there are only 1 billion valid numbers. There are billions and billions of total cards out there that have been issued, right? And so you might wonder, well, wait a minute, if the leading 6 are determined by the network, and I could determine, say, which issuer you had, there's only so many account numbers, maybe I could just like guess them and get your card number, right? And actually that is somewhat valid, except there are other security measures, especially in the day and age of internet banking. You have the CVV number, the security number on the back, you need to know the zip code, there's a bunch of other information. It's very unlikely to guess all that stuff together, okay? But there are only a billion within an account there. So what I want to do is run through how that checksum is determined, and if you like, you can take out your own card and do the work here along with this one here. I'd ask for a volunteer, but of course, putting your credit card number on camera would be an outrageous thing to do here. Okay? So let me explain the algorithm for determining that checksum. All right, so I'll switch over here, and we'll compute it with this specific one. And I'll talk about what the purpose of it is as well. Okay. So, what we're going to do is look at the first 15 characters, and I'm going to do a simple bit of arithmetic, compute a number, and then that number will tell us how to figure out what the checksum should be. Okay? So we'll do it, and then we'll hopefully convince ourselves that 6 is the correct number that should belong there. So what you do is write out the first 15 numbers, on your card number. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 9. I think, is that the first 15 I have on the board there? I checked this, so it won't work if I put something else. And then I'm going to put like a box here. This should be a 6. Once I describe the algorithm, we'll see that it indeed is a 6. So what do you do here? You start from the first digit here, and every other digit, write down its double. Okay, just double it and write it down below. Okay, so 1 doubles to 1, 3 doubles to 6, 5 to 10, 7 to 14, 1 to 2, 6, 10, 18.
Shouldn't 1 double to 2?
Oh, yeah. Yes, thank you. Yeah, that's quite a mistake to make. 1 doubles to 2, thank you. Yeah, actually, this is great too. If you do this wrong, you will get bad output as well. Okay. Then, after I've done that, the numbers that were not doubled, I just write them down in their original value. So 2, 4, 6, 8, 2, 4, 6. Just write those down, okay? Then what I'm going to do is add up all the digits that I've written on the board here, okay? I'm going to be very careful. Add up the digits that I've written, not the numbers. 10 will only contribute a 1 and a 0. 14 will contribute a 1 and a 4. 10 will contribute a 1 and a 0. 18 will contribute a 1 and 8. So add up the digits after I've performed this procedure, okay? I believe these add up to 64. I don't have a calculator in front of me. It's worth double checking that. I mean, if I just lie to you, then the solution works here. Anna's checking on her hands here. We'll give that a minute. We're not in a hurry here, so. Oh, I added wrong. Yeah. I wasn't adding digits. Remember, add digits, not quantities. I should have brought a calculator with me. No pressure.
Yes.
64, okay, it's confirmed from the audience. These add up to 64. Okay, the checksum, this value is a value chosen so that when it's added to this thing here, the total is divisible by 10. That's the requirement. So once I perform this whole procedure, in fact, if I were to continue this procedure with the 6, which is known, then I would get 70, which is divisible by 10. So you can either take your card and check this and you'll get a number divisible by 10, or if you just make up 15 random numbers, the checksum should be whatever would go here to make the digits here add up to something divisible by 10. Okay? So this should be 6. Okay? That's how the checksum value is computed, and so as I pointed out, it is not determined. It's not a random piece of information. It just follows from the other 15. Once they're set, the checksum is automatic. Okay? Now you might be interested in like, well, what is the purpose of the checksum? Because this is a very cool and very interesting thing used in computer science and discrete math and all over the place. And this is a very, very sort of basic version of it. So the idea of the checksum is as follows. Suppose you gave your credit card number and you made a mistake, right? So suppose in this list, I made the following mistake, that I put in a 5 here instead of a 4. Okay? So that was an error. When I do this whole addition up, I'll get 65 plus 6, I'll get 71, which is not divisible by 10. So immediately this can set off, red flag that, oh, this is not a valid credit card number. It's not, you made a typo most likely, or you tried to enter some nonsense, because the checksum was not correct, okay? Now, of course, if I also alternatively made a typo here to turn that to a 5, it would still add up to 70. That can happen. Checksums are not perfect. But they will identify a potential error like this. This was originally 4, so let's go back to 4. Okay? Nowadays, with internet banking and so on, and all these things being done electronic, you can do additional checks by, you communicate with the issuing agency quickly. But in the old days, some of you may remember, I certainly do, the time when credit cards were, there was a physical device that kept track of them, and you could be checked on the spot with the checksum that at least wasn't entered correctly in the first place. You type the number into a keypad, say. Okay? Now, there are other checksums you could make, right? Why did we double every other digit here? Why didn't we just add up all these digits here and make the total divisible by 10? That also would be a simpler checksum. There's an extraordinarily clever reason for doubling every other one. The reasoning is the following. The reasoning is that the most common mistake you'd make when entering your credit card number is to transpose two numbers. That's the most common thing. At least that's what would be believed. So suppose I transposed 5 and 6, okay? So this became 6, this became 5. If my checksum was the simpler version where I just added up all these numbers and made the result should be divisible by 10, this transposition would not change the checksum. It'd still be valid. But in the model we're looking at, this would become a 12, this would become a 5, and that sum definitely would no longer work with this checksum here, okay? So doubling every other one helps us identify flipped ones particularly, okay? It highlights those as well. Again, it's not perfect. You can make multiple mistakes in such a way that they cancel out, but this is to check flipped ones here. And I explained this to my kids, and they said, well, what if the two digits next to each other had the same value, and then you flipped them? Wouldn't it cancel out this difference here? Yes, but if you transpose two digits that have the same value, then you still got the original credit card number back, and so there's no issue whatsoever. Okay? Anyway, so that's a checksum. They're used all the time on the internet. When you download software, there are checksums that check if the software is valid by taking all the bits in the piece of software, running it through a simple algorithm, and saying, hey, does this output correspond to the output that we recorded on our website? This is one way of verifying that your code is really what it says it is. Okay? But again, there are ways of potentially getting around checksums, right? So it's not a perfect method. Okay? All right. So that's that. I want to take a 2 or 3 minute break here. The hour here at UM has sort of ended, and I want to give people a chance to escape the room if they need to, or stick around. So I'll take 2 minutes before I go to the next slide, and I'll be on camera here still. But you guys are welcome to stay if you're already here. So.
Can we switch the one into two?
Good question, Thomas. Yeah. In the beginning here?
Yeah.
So yeah, okay, that's great. So imagine I switch the 1 and the 2 here. So this becomes a 1, then this becomes a 2. Then this becomes a 4, right? And this becomes a 1. And so originally I only had a total of 3, now a total of 5. So it can be a pretty big change. And then the 6 would no longer work. Right? So, yeah.
Thank you.
Yeah, you bet, Thomas. See ya. Well, maybe I'll erase this in the meantime. Okay. While I'm taking a minute here, those of you in the chat, is the video and audio quality passable? Can you follow and hear everything you'd like to? The cyan marker. Okay, I won't use that marker. Yeah, I had a suspicion it wasn't very good. So.
The green?
Yeah, the green wasn't very good, was it?
No.
Yeah. Let me check. I have some other greens. Let's see if this one's any better. That's still not very readable. I can restrict myself to the black and red. Audio video quality is good? Awesome. Thanks, Mark. We have classes just ending here, so people are moving around, so I'll start back up in a minute here.
I've already learned something about credit cards.
Yeah, Patrick, yeah, you might have missed it. I know you know what a checksum is, right? That last digit is literally a checksum, and it's a very simple algorithm that works on the thing there to, well, to compute it. It's like one of the best ways, I think, to introduce what a checksum is and how it works. It's so much simpler than like a, not that MD5 is very, particularly hard to explain, but like there's a real algorithm, and this is like, you just kind of add up every other digit in a special way, and it works, so. Nice. Oh, I've got a calculator now. Okay, that's great. Thanks. All right, well, I think I'm about ready to jump to the next slide here. So why don't we continue what is now the second hour. Okay, great. So we've been counting social security numbers and counting credit card numbers, and another very common thing to count that's highly relevant to our daily lives is passwords, right? Making your password secure comes down to the counting principle in disguise, how many different passwords there are, given certain restrictions. And this will be a common theme throughout these slides. This will return on several occasions here, okay? So on the left side of the slide, I looked up the original ASCII definition of ASCII characters. I think this chart's from like the 50s or early 60s or something. It's been around for a long time. Okay, I don't know my computer science history as well as I should, so. Anyway, this is old. It's been around for a while. And what I've highlighted in red are the valid characters typically in passwords, okay? So you have your uppercase and your lowercase letters. You have your numbers, and then there's a bunch of symbols that are valid as well, right? I'm sure you all remember entering a password on a website and says, must have lowercase, must have uppercase, must have number, must have symbol. This is the typical list, okay? There are 95 of these ASCII characters, okay? So I want to do some comparisons here and talk about password length and the alphabet from which you're choosing, okay? So let's flip over to the screen here. No more green. And I want to answer the following question. So the first is, suppose we're just making a password out of lowercase letters, and we're going to make one of length 12. How many total are there? Well, we can use the product principle again here to answer this question, right? The first character has 26 options, the second character has 26 options, the third character has 26 options, and in total, there are 26 to the 12 different passwords from this space, okay? So this is alphabet of size 26, and this is length of password. Okay? So these are the two pieces of information. Okay? And I computed these ones as well. I think it's handy. This is approximately, we have to use scientific notation here if we want to compare. 9 times 5 times 10 to the 16th. So something 17 digits long there. It's big. It's a huge space of passwords. Okay. Now, what if we change the problem and we're going to choose from a larger space of characters, so not just lowercase letters, but we're going to make them a bit shorter. So we're going to have 8 character passwords instead. Okay. Well, in that case, we just use the exact same model. We have 95 characters, and length 8 will multiply 95 by itself 8 times. So you get 95 to the 8 such passwords, okay? So again, here now my alphabet is of size 95, yes, right? My alphabet, right, these ASCII characters, and the length is 8, okay? Maybe I'll ask the audience of the chat, without computing this one, any guess which of the two is larger? There's no reason you should, have a good intuition here. But which of these two is larger? 26 to the 12 or 95 to the 8? Which do you think is bigger? Anyone care to weigh in? Ryan, what do you think?
Second.
You think this one's the bigger one?
Yeah.
What
I'll
else?
say first.
Yeah, I'd say
Zhuzha says first. Noah says first. Okay, so yeah, good. So actually, I'll have to write it out.
Can I guess equal?
Equal? Yeah, that's okay. That's like a punchline, right? Yeah, they're not equal, but yes, that's a good guess. So the second one is 6.6 times 10 to the 15th. So actually, Van's not far off, depending on how relative order of magnitude. They're not that far from each other, right? This is instead 16, length 16. Number of options. What I do want to highlight here, though, I think at least, is I think maybe it's surprising that there's fewer here, right? Here you have this enormous, we like exploded our alphabet. Yeah, we made it a little shorter, 4 characters shorter only, but the alphabet was like more, almost 4 times as large, and we didn't quite come up to this level here. And so if you were just to restrict yourself to small alphabet, say 26 lowercase letters, as long as you made the password long, you can easily beat having a big alphabet here, okay? So in some sense, and this is familiar, of course, to many of us, it's the length of the password that's the key part here, okay? The character space is, of course, also important, okay? But if you were just to choose lowercase letters and maybe make it length 100, then the space of possible passwords, well, I'll go out on a limb and say will never be broken, right? It's not searchable in any reasonable amount of time, okay? All right. We'll return to this. Ryan will talk to us a little bit about what if we add restrictions that we typically see that each password needs to contain both an upper and a lowercase character and things of that nature. That changes the space, and you can figure out exactly how many of those there are as well. And there's an interesting punchline there as well. Okay. All right, so now we've been talking about strings, essentially, right? The social security numbers were strings of digits of characters 0 to 9. So were credit card numbers. And in the previous, we had strings of characters from this ASCII alphabet or from lowercase letters. So now I want to talk about binary strings, a fundamental object in computer science and in discrete math. And all a binary string is a sequence of zeros and ones of whatever length you're interested in, okay? So in this universe, your alphabet is very small. You just have ones and you just have zeros and you just glue them all together. And you can see a couple simple examples in this slide. I'll jump here. Well, I won't necessarily use the one written there, but here's some examples. Example binary strings, like 1, 1, 0, 1, 0, 1, 1, 1 is a binary string of length 1, 2, 3, 4, 5, 6, 7, 8. Okay, so length 8. And 1 by itself is a binary string of length 1. 1, 0 is a binary string of length 2. That's not 10, that's the binary string 1, 0. Okay? So we want to count binary strings just in the same way we counted passwords. This is something important to do. And actually, it will be a very common theme throughout the lectures. Counting binary strings and working with binary strings is a very popular activity in discrete math, and it is of a great deal of importance as well. As many of you probably know, computers basically operate on binary. They operate, well, there's electronics in the background, but we're recording pieces of information that are either 1 or 0, either true or false. There's just 2 cases to work with. Okay? So the question asked here, how many binary strings are there of length 9? Right? Well, this is no different than our password question. We have a string of length 9. I haven't used this model yet. 1, 2, 3, 4, 5, 6, 7, 8, 9. Right? And each of these slots has 2 possible options. It could be a 1 or a 0. Right? 1 or 0, 1 or 0, all the way to 1 or 0. Right? And this is a product principle question, right? In step 1, I have 2 choices, a 1 or a 0. In step 2, I have 2 choices, a 1 or a 0. And in step 9, I have 2 choices, a 1 that should be an or, a 0. So in total, we're going to have 2 to the 9th, right? 2 times 2 times 2 times 2, the length there. This is 2 to the 9th, binary strings of length 9. Okay. All right, and what if I'm interested in binary strings of length 9 that must begin with 1, 0, 1 in them? Okay? So I'm interested in binary strings that look like this, where there's a 1, then there's a 0, then there's a 1, and then I'll put like a little star here. This is just a different model than what I put above here. 6, 7, 8, 9. Right? There's my binary string, and all of these have 2 options each. Okay? And earlier on, when we were talking about the product principle applied to deli sandwiches, we had this notion of we like to pretend in math sometimes, right? And we're going to do the same thing here. And you don't really have to pretend, but this is of length 9, but what's the important part here? It's the remaining 6 here. These 3 make no effect on the total number of strings. They're fixed for me. I don't have any choices as far as the product principle is concerned. Or I could say, I have 1 choice, 1 choice, 1 choice, because it's made for me already. I don't think that's particularly illuminating. It's just these 6 choices I have. counting binary strings of length 9 that start with 1, 0, 1 is the same as what? Counting binary strings of length what? Of length 6, exactly, right? You can just ignore this leading part here and just say, oh, every binary string of length 6 here can be glued onto this at the front, and they'll all automatically be different. Okay? So there are 2 to the 6th of these. Okay? And actually, we can further modify this problem. What if I wanted to know the number of binary strings that ended with 1, 0, 1? Or had 1, 0, 1 in positions 2, 3, and 4? Or even spread out position 2, 5, and 9? Just ignore those, right? Anything that's fixed for you in advance doesn't affect the total number of outcomes you can have here. You only have choices in these 6 positions here, okay? All right. Did I write down the number? What's 2? Yeah. Oh yeah, okay, maybe this is worth stating. How well do you guys know your powers of 2?
What is it?
2 to the 9th?
512?
Yeah, 512, and actually, because this is worth knowing, Patrick, do you have 512 memorized?
2 to the 10 is 1,000.
Yes, very good. The very, very popular 2 to the 10th is 1024. This is something worth memorizing, I think. This comes up a lot in mathematics and in real life. And if you can work from here, it's like, oh, well, 2 to the 9th is half of that, so, and you remember 512 is one of them. 2 to the 6th, well, you can do this step a couple more times. I tend to remember the first 6 personally, and then I start to run into trouble. I think this one should be 64. Okay? So of course you lose a lot of options when you make this additional restriction that the first 3 are fixed. But that's not surprising, right? I've lost 2 times 2 times 2, 2 to the 4th options here. Okay, and that's exactly the gap between, what? 2 to the 3, 2 to the 3, thank you, yeah, 2 to the 3, yeah. All right, I promise you exponent rules were important, and here is one place where we use them. Okay, let's go on. Yes, okay. So I want to talk about hexadecimal strings now too, because these are very fun to work with as well. Okay, so binary strings are 1s and 0s, decimal strings are 0s up to 9s, and hexadecimal are strings that come from an alphabet of 16 characters, okay? And those 16 characters usually are denoted 0 through 9 and then A through F. So A is our 11, B is 12, up to F it counts for 16. So you can write down any number you want in hexadecimal as well. So that number there, 2, 4, 3, F, 6, A, blah, blah, blah. If I'm not mistaken, that is the first so many decimal digits of pi in hexadecimal. Okay? You can check that. I don't remember exactly off the top of my head if that's right or not. And what does that even mean? Don't worry too much about it. We'll just look at hexadecimal strings. This table here gives some examples. So 63 in decimal, just an ordinary number 63 we work with all the time, can be written as 0, 0 followed by a bunch of 1s in binary. And in hexadecimal, that can be written as 3 times F. And you may be wondering, how do I know that those are the same? How do I go between one and the other? It's not hard to show how to convert between these different bases, but that's not my goal in this class at all. We're not going to cover that. We're just going to talk about hexadecimal strings on their own, because they're cool and interesting and commonplace. Okay? But just to give you an idea, every number has a representation in these different formats, and there's an algorithm for going between the two. Maybe a year from now, when we do this again, we'll talk about how to do that. It's a common exercise in discrete math. Okay? All right, but I just want to talk about about hexadecimal strings here. Okay? Maybe before I do a problem with them, I want to talk briefly about why hexadecimal. Like 16 seems arbitrary, and there's pretty good reasons for it. So binary is, like I said, sort of the language of computers. Thinking in 1s and 0s is very convenient, and it's the way that data is encoded in computers in some fashion. But if you were, say, a programmer or someone working with data, binary is extremely unwieldy to work with, right? Just look at the number 63. Look how many digits or bits we needed to write down to describe it. It was lengthy, right? But hexadecimal, on the other hand, is very short, right? Even for 3-digit decimal numbers, we were able to get away with 2 hexadecimal digits there. Okay, so that means hexadecimals may be more convenient than binary, but you might say, well, wasn't decimal already more convenient? Well, yes, I mean, we are very comfortable with decimal in our ordinary lives, but when it comes to converting between these formats, which again, I'm not going to talk to you how, it's easy to convert between binary and hex, much easier than between binary and decimal, in some sense. A lot of that comes down to the fact that 16, what's 16's relationship with 2? it's a power of 2, right? That's very important. We like powers of 2 in computer science exactly because our base is binary, okay? So that's one of the reasons we use hexadecimal. When you get comfortable enough with these things, many people, not I, but many people can recognize in hexadecimal quickly convert to decimal in their head. It's not that hard to do if you know your powers of 16. It's not that easy to do either, but yeah, no.
Missed it, but what does the F have to do with, like 3F?
3F, okay, good. So what is 3F? So F is our number 16 in hexadecimal, right? So the alphabet in hexadecimal, there are 16 like letters, or 16 numbers, 0 up to 9, and A through F. A is 11, B is 12, F is 16.
Oh, I see, so letters.
Or 15, I'm sorry, it's 15, not 16. 0 up to 15. Yeah.
So letters just represent a certain number.
Yeah, because we don't have a symbol for the number 15 without writing it in decimal 1/5. So we just use F for that. We could make up new symbols if we wanted to, right? And in fact, there are other languages and cultures that use different bases, right? The Sumerians used base 60. Their numbers had 60. There was a 60s place. Okay. I don't know if there's any culture that actually used hexadecimal. Except for someone's logging into Wikipedia here for me, but anyway. So yeah, so hexadecimal in ordinary life, it maybe isn't that convenient, but if you're working with binary a lot, it's a really quick way of encoding those things. And let me actually, what I want to talk about are some examples. Okay, because hexadecimal, you do see them all over the place, you may not realize it. But for instance, on the web, right, when we have a website and we have different colors on it, when you write code in HTML and make a web page, which actually we don't really do that much anymore, but there was a time, when I was younger at least, that we did, colors are encoded with a hexadecimal string. And they look like this, and this table actually shows some of them. Each of those colors, the number in there, written in hexadecimal, corresponds to that color. That's how they're encoded, right? The hash in front of them is just a way of saying that this is a hexadecimal string. It doesn't contain any content, okay? So a question might be, okay, well, according to this encoding, a hexadecimal string of length 6, how many different colors are possible on the web, right? Each of these is a different color. I mean, obviously, some are similar. You can see the FFBBED and FFC1CB are very similar in color, and you can even see that their values sort of are somewhat close to each other as well. Okay? But let's just answer the question of how many there are. Okay. So I'll switch over. And this is very simple as well, compared to like the binary string questions. It's just exactly the same flavor. So they're of length 6, and each of the individual characters has 16 options. So the first hexadecimal character has 16 options. So does the second, the third, the fourth, and so on. There are 6 of them, so that's the total number of those. Okay? Some number, I don't know what that is computationally, but that's how many different colors we have access to on the web. It's quite interesting, there are style guides for websites, and there are many colors they recommend against using and using together, but anyway, this many different numbers are available to us. Okay? Some of them, sometimes you memorize, I think black is maybe all Fs, something like that. I see a nod, maybe I'm wrong, but yeah. I think there's surely an algorithm between colors and their RGB value and their hexadecimal string. I don't know what it is, but I'm only interested in the question of counting them. Okay? There's another very common place where hexadecimal strings are used as well, and that's in IP addresses. And actually, I'm interested in IPv6, which is a more modern protocol than the string of four triples in decimal. Okay? So modern IP addresses, so these are ways of identifying computers on the internet and all over the world. Each gets assigned essentially a unique code. Let's keep it as simple as that. And those codes are written in hexadecimal, or in binary in the underlying, and they're lengthy. They're represented by 8 groups of 4 hexadecimal digits. So your computer has a number that, I won't write that one down again, but is made up of 8 blocks of 4, okay? Okay, so this has 4 hex digits. And there's 8 blobs. Okay, so here we need a couple of steps in order to solve this problem here. And there's more than one way to solve it. But my question as well is, how many possible addresses are there? And the reason we have this modern protocol is the old protocol is running out or ran out of space, right? I mean, when the original IP addresses were invented, there were not nearly as many computers and devices that need IP addresses as there are today. We'll see this will sustain us for quite a while. The number that here is absurdly large. Okay? Okay, so how do we figure this out? This one's a little more complicated than before, right? And there's a few product principle approaches to this. One, we can notice, well, there are 8 blocks of 4 digits, so how many total hex digits are there?
32?
Yeah, there should be 32, right? 32 total positions. In other words, we're looking at a length 32 hex string. Hexadecimal strings come from an alphabet of 16 different characters, 0 through 9, A through F, okay? So using the methods we've been using, we can just quickly answer this question as, well, it's 16 times 16 times 16 times 16, 32 times. Okay? So there's the number of IP6 addresses. I did not compute this. If someone has a computer in front, I'd be interested in what this is in scientific notation. It's big. And then we'll answer the question in a slightly different way too, just because it's of some interest. So, did you get it, Ryan?
Yeah, 3.4 times 10 to the 38.
38?
Yes.
Yeah, that sounds about right. Okay. So 39 digits long this number is. There's a lot of them. There are not nearly that many computers, and there never will be. I don't think, I mean, yeah. So let's answer this in another way using the product principle as well. Okay, a slightly different approach here. How did we get this 32 in the first place? Right? We multiplied 8 and 4. Right? Well, what if we instead have said, well, wait a minute, this thing really is from an alphabet whose letters are blocks of 4 hexadecimal digits, right? So in one of these blocks, I could have, 9FA3. Right? That lives inside of that block there. And there's a bunch of different options for this block, a bunch of different options for this block, for this block, for that block. Okay? So in this case, instead of saying, oh, there's 32 positions, each of us have 16 options, we can instead say, well, there's 8 positions. Right? These 8 blocks, and each of those blocks comes from an alphabet of size what? How many different ways can I fill in one of these? 16 raised to the 4th power, right? So there's 16 raised to the 4th power blocks, different things I can fill in here, and there are 8 of them, so I multiply 16 to the 4th by itself 8 times. And we've already been talking about power rules, something always good to remember. In this case, you don't add powers, but you multiply them. And so this, of course, comes out to 16 to the 32. Okay? It's just another way, of course, of solving the same problem there. We can break it down into think of these as our letters, which are quite large letters, and there are 8 of them. Okay? All right. Yes, let's go on. Okay, so this actually just summarizes a bunch of the things we've already talked about. Suppose I'm talking about a string of length k now. So k is some unknown number. Instead of being specifically length 32 or length 6, I'm talking about length k. If you have a binary string and its length is k, there are 2 to the k of them. 2 options for each of the k positions. 2 times 2 times 2 times 2 to the k. Okay? For hexadecimal, our alphabet has 16 instead of 2 characters, so it's 16 to the k. Okay? I don't think I even need to write these out, right? This summarizes the things we've done multiple times. And then most generally, suppose you have a string of length k, and the alphabet has n characters in it, right? N characters might be 26 letters. It might be 95 ASCII characters. It might be 2 binary bits. It might be 16 hexadecimal characters. Anything like that. Then it's just n raised to the k. N times n times n times n, k different times. So in the theorem here, C is, of course, the most general. That is the answer to all these string questions. If your alphabet has n different letters in it, and your string is of length k, then you will always have n to the k different possible strings there. Okay? So that summarizes these string type problems, and that is the product rule in disguise as well, the product principle. In fact, I think that's what's on the next slide. Yes. So this is, you can even be trickier than that. What if your alphabet updates at each point in the string? Okay, so you have a string of length k, but you're not using the same alphabet at each point. Okay, here I want to write some things out. So here, we're going to have an alphabet, or a string of length k. So let's say we have k characters. And in each step, I'm selecting from a different, potentially different alphabet. So in the first step, say there's n sub 1 different letters in my alphabet. Maybe that's 7, right? Maybe I'm first choosing a vowel, or a day of the week as my first character. And then in my second position, I'm now choosing from, say, the numbers 1 up to 10, or 1 up to 9, 0 up to 9, 10 different options there, right? Maybe it's a password. And then the next one, maybe this is a hexadecimal string. So say there's n3 options, and then n4 options, and then all the way down to n sub k options, okay? If all those n sub i's are all 2's, then this will be 2 to the k. If they're all 16's, this will be 16 to the k. If they're all 26's, it's 26 to the k. But there's nothing preventing us from altering the alphabet at each step and having this product here as the number of strings of length k. Notice, I call this the general product principle. And why is this the general product principle? Well, it's the same thing. So, general product principle. Well, remember the product principle. It said that if you have A ways to do step 1 and B ways to do step 2, then there are A times B ways to do the whole procedure. Here, instead of thinking of these as strings, we can think of this as a procedure. Suppose there are n ways, oh, no green. Actually, maybe this green's better? A little better, yeah. Say there are n1 ways to do step 1. Ways for step 1, n2 ways for step 2, and all the way up to nk ways for the kth step. Then the total number of ways to do your procedure, like the very early example we did with creating outfits. Maybe you have k different articles of clothing you're dressing yourselves in, right? This is the number of different shirts, times the number of different hats, times the number of different socks, times the number of different shoes, and so on and so forth. You just multiply all these things out, okay? We've already established this throughout, but this is stated in its most general form here, the general product principle. So it either corresponds to strings or to number of ways to do something. Obviously, those two things are the same as each other. They can be described. One describes the other. Okay, so what's next? Yes. So one very simple instance of this is how many 20-digit strings have no two consecutive digits the same? Okay, there'll be a slight tweak in how our alphabet works here. Okay. So let's diagram this on the board here. And I'll keep this written up here so we can sort of identify what's n1, n2, and so on. Okay, so I'm interested in a 20-digit string that doesn't have two of the identical number next to each other. So let me write down one that doesn't count. So 3, 5, 2, 1, 4, 4, 3, 6. Okay, I don't want to write down 20 digits. It's very long. This is invalid. Because it had two 4s next to each other. Okay? And these are strings, not numbers, so I will allow myself to start off with 0. Okay? But if I don't allow that, it only changes the problem slightly. Now, I would like to know how many strings of this type there are. Well, notice that now this model is what we need to do, because my alphabet changes at each step of the way, right? Suppose I'm writing down my string here. Okay, I should write anything but a 6 there. Let's put a 5 there. And I'm interested, like, what's the next character I can put there? What's my alphabet at this point? Right? What letters or numbers do I have access to for the next digit here? All but one, exactly, right? I can use 0, 1, 2, 3, 4, not 5, 6, 7, 8, 9, right? So 5 is out because I'm not allowed to do repeats here. Okay, so say I chose 0. Then for the next one here, what's my alphabet? All but one, this time I'm allowed 5, but not allowed 0, right? So here also, I have an alphabet 1, 2, up to 9. And then say I chose 3 here, then my alphabet here would be everything but 3, right? So you see my alphabet itself is changing slightly at each step. But what is nice here is in this model, what are the values of these NIs?
Mostly 19s.
Uh,
Nines.
Nines? Do you mean? Yeah. The alphabet's not 20 characters, yeah. So mostly nines, Van says, which is a very good answer. Except for this first one where we have 10 options, right? When I write down the first digit here, there are no restrictions, and I can do any one 0 through 9. But all the remaining ones here, I lose one character, that was to the left of it. Okay? So I have 9 options, 9 options, 9 options, 9 options, 9 options, and so on and so forth. So our total answer here is going to be, my alphabet is of size 10 in step 1. In step 2, my alphabet is of size 9, because I can't use what I used here. And in all the remaining steps, it continues to be 9 options, right? Because I always have one lost. So that's the total number of strings of that type, okay? What I want to get at here, this is a subtlety. These values, ni, the number of options that I had, more or less stayed constant. It was 9 almost at every step. But the actual alphabet itself was changing, right? In this step, the alphabet was 1 through 9, 5 excluded. In this step, the alphabet was 1 through 9. In this step, the alphabet was, in this step, it was 1 through 9. In this step, it was 0 through 9 without 3, and so on and so forth. So the alphabet changed at each point. But the alphabet itself isn't what's important. What is important? Not the alphabet itself, but yeah, the number, how big the alphabet is. Do we have 10 letters, 20 letters, 50 letters? That's what matters. What they actually are, symbols are interchangeable, right? It doesn't actually matter. Okay? So this is the number of strings of that type. Okay. I'm going to get a sip of water here. All right. Okay. This is a personal favorite of mine. It takes a little bit of background to explain what's going on. But we can answer this with our generalized principle. I'll leave the generalized principle on the board here. And I'll explain this problem to you. Okay? So during the pandemic, I was at home a lot, like everyone was, and I was up late, like many of us were too. And I found myself watching a lot of sumo wrestling at that time. And it's a fascinating sport, and I could talk to you for hours about it. I won't do that now. Instead, I hope you'll indulge me, and I'll give us a sample combinatorics problem from the sport of sumo. Okay? So sumo has different divisions, high and low divisions in professional sumo. The top level is called makuchi. That's just the name. It's not important to the problem. But the way it works is there are 42 wrestlers. They're called rikishi in that division. And in a tournament, which is a basho, it's called, these wrestlers are paired up each day. Okay, so you wrestle once per day against one of the other, 41 other wrestlers. You don't wrestle yourself ever. And the way that it works in a tournament is you never wrestle the same person twice. So each day you're wrestling someone different over those 15 days. Okay, and so when I discovered this format, I immediately was like, well, can't they get trapped sometimes? Like, what if they arrange it in some way and then at the last day it's like, oh, I can only pair you against someone you already wrestled against. So I was like, well, how many ways can you actually pair them up in the first place? Just day one, there's 42 people, how do you pair them up with one another? Okay? And I want to answer this question using this generalized product principle, essentially. So our alphabet of sumo wrestlers sort of changes at each step. Okay? So let's look at it this way. Let's just write down our sumo wrestlers as 42 points on the board in a row here, okay? So different wrestlers are different individuals, so they're distinguishable objects, but you could also put them in order by their rank. They are strictly ranked from 1st to 42nd. There's a yokozuna who's at the top, and there are different categories of sumo, like the next, there can be multiple yokozunas, but okay, I don't want to go too far into this point. But let's rank our wrestlers here, okay? And try and figure out how to solve the problem this way. Okay, so here we have 42 rikishi. I think I spelled it correctly, right? Rikishi, yeah, okay. And I want to know how we can pair them up. And let's answer this with basically like a simple algorithm, okay? So say I'm the person that's deciding how they're going to be matched against each other. What I'm going to do is say, okay, I'm going to start with the first highest ranked wrestler that hasn't been matched yet, okay? And choose an opponent for him in the first day. How many opponents does this person have, potentially, before I've done anything? 41. They can't be paired with themselves, right? But there are 41 other people, okay? So, and I'll even draw like a line. Let's suppose he was matched with that person. I could draw that line to anywhere else, anywhere I wanted, okay? So 41 options for first. I'll just call it first step, okay? Because we'll see that this gets a little subtle in a moment, okay? Okay, so now let's go to the next rikishi, the second highest ranked one, okay? How many options does this person now have to be matched up with?
39.
Yeah, 39, good. And where'd you get 39 from?
Because those two people are taken out and the person that needs a match can't be counted.
Fantastic, right? We lost two people, they've been matched, they can't wrestle anyone else. This person can't wrestle themselves, so we've lost 3 of the 42 as far as this problem is concerned. And so there are now only 39 options for second step. In this case, this was 41 options for the first wrestler and 39 options for the second wrestler. I very particularly didn't write wrestler here though, because imagine that this person was just matched with the third ranked person, right? Then, when I get to this person, there's nothing to do. They have already been matched from some prior thing, so I just skip them. So my algorithm just runs through and looks at the next highest rank who has not yet been paired with someone. Okay, so now I'm at this person. How many people can be matched with them? 37, we just lose 2. Each time I'm matching someone new, 2 prior people have been lost, right? From what was already lost, essentially. That's one way of seeing it. They're also lost, but this person is no longer double lost. I don't know if that makes sense. They're lost from the matching. This person and this person are different from each other. The easiest way to really see it is you're never gonna have more than 41 options because you can't match yourself. And for all the prior matchings, 2 are lost because they're paired with each other. So then there's 37 options.
Cory,
Yeah.
you're on the small screen right now.
I'm in the small screen. Oh, thank you, Ryan. I will switch over so you guys can see this a little bit better. Yes. 37 options for the third step. And so on, right? We can continue this process. What's the process going to look like near the end? Well, some of these people might already be going matched back like that to someone, right? Imagine I finally get down to this person here. Even this person could potentially be matched, right? In fact, let's do it this way. This is a little more interesting. So say I get here, and there's only 2 people left at the very end, right? Everybody agree that at some point I'll only have 2 left? Yeah, it's important that there was an even number of wrestlers. There were 42, so they could be matched in the first place. And at each point, 2 people are sort of taken out of contention. And at the very end, I get to, okay, this is the highest ranked so far unmatched person, and there's only one person for them to match with, so how many options will there be in the final step? Just 1. There's no real options, right? So it continues down until there's 1 option it's not important to the problem, but can we figure out which step number that is? How many times will it be created a pairing?
21.
21, yeah, there's 21 pairs. Yeah. What's that?
However many odd numbers there are.
Yeah, divide this by 2, in fact, right? Maybe everyone sees as well that if we had 100 wrestlers, we could follow this procedure as well, right? So down it'll be for step 21, right? At the very end, we've matched up all 42. The last step will be matching the 2 unmatched there. Okay. But this is a product principle question, or in disguise, it's actually a string question, right? You're writing out a string, and that string is what? In the first position is the name of the wrestler that will pair with this guy. In the second position is the name of the wrestler that will pair with this guy. It's a little trickier than that. In this position, you don't write anything because they've already been matched. So it's better to think of this just through procedurally through product principle. But what will be the answer if I figured out all these quantities here? It's just the product of all those numbers, right? If there were 41 options for the first person to be matched, then there's 39 options for the next unmatched person to be matched. Not necessarily the second, right? Keep in mind this guy could be matched with this guy, and then the next person would be this one to choose, right? But it's certainly 39 choices no matter what. Okay? So the total number of pairings is 42 times 39 times 37 times 35, all the way down to times 3 times 1. Okay?
Would it be 41 in the first one?
Oh, of course, thanks, Joel. Yeah, 41. Absolutely. Yeah, there were not 42 choices. Yeah. So it's that product there. The product of all these odd numbers descending from 1 less than this here, and I did write down what this was in scientific notation because it's a bit hard to see. Oh, yeah, okay. It's 1.3 times 10 to the 25. Okay, it's a hilariously large number. So like, you don't have to worry too much. It's incredibly unlikely, even if you're assigning randomly. Well, okay, that's a little more sophisticated. We'll talk, Ryan, actually, I'll talk to you guys that at about hour 3, a little bit. But there are a lot of options, so ways to pair these up. So even if you've gotten 14 days in, it's very likely you can avoid, and yeah, I mean, it's certain you can avoid matching these up. In fact, you might ask, and I originally wanted to ask was, okay, there's that many ways to pair them up on day 1. There should be that many ways to pair them up on day 2, but that's not quite right, because on day 2, I'm not allowed to match anyone the same. So this particular arrangement I gave, I can never give this exact arrangement again, but there are other, I can't give any arrangement where this person's matched with this person, or this person's matched with this person. They all have to be different in day 1. So, in day 2. So day 2 is actually quite challenging to figure out how many ways you could pair them up after you've done one in the first day. Actually, Van will answer that, how many ways to do it in the second day. Not explicitly, but it will come out of his answer. But then you say, okay, we can do the first 2 days, how many ways can we do the third day? It gets harder and harder and harder to compute. It's not impossible, though. Okay. All right, so yeah, that was sumo. Yes. All right, so let's jump to the next sort of subsection here. Permutations and factorials. I'm going to introduce both of these concepts here. And the ultimate permutable object is the Rubik's Cube. There's almost nothing better you can talk about. I won't answer this explicitly, but I will equip you with the tools to do it. A natural question with the Rubik's Cubes is, hey, how many different configurations are there, right? We've heard there's a lot. There's something or other quadrillion. We have almost already the tools we need to figure that answer out. You need to analyze the cube a little bit in order to do that. But I want to equip you with what you need in order to answer a question of this type. Okay, so, first question, yes. I want to go back to hexadecimal strings for a second here, okay? And I'm going to keep this on the board for a while. This is really handy, this general principle here. Imagine now I want to make a hexadecimal string and say just length 4, right? Just a short one. But I never want to repeat a character, okay? So I want to write down a hexadecimal string that looks like, I'll write a couple of them here. Sumo anymore. That looks, say, like A3F4. Right, there's one hexadecimal string with no repeats in it, okay? Or AB09, okay? But something like 113A or ABBA, these are bad, right? These are invalid. These are invalid strings. This has a repeat 1-1. This has a repeat AA and BB. Let me switch the board here. But these ones are good, right? These are length 4 and they have no repeated character in them. And I want to answer how many of these there are. Okay? And we can again use our general product principle to answer this, right? At each step, our alphabet is being updated. It's very similar to the length 20 digits where we had no 2 consecutive, but a little bit different, right? So it's going to have length 4, and I'll continue writing it in this model here. And if we just write from left to right, how many options will we have for the first character? 16, no, right? Remember the alphabet has 16 characters in it, right? So there's 16 characters for the first one. And then my restriction on the second character is that it simply not be what the first one is. So now I have an alphabet of size 15 at my disposal. Like before, the alphabet itself here depends on what this is. If this is an A, then this is everything but A. If this is a 1, this is everything but 1. But it's 15 no matter what. The quantity is what matters. Okay. How many options are there for the third then? Yeah, now 14, now it dropped, right? We have 2 restrictions. You can't reuse those at all. So 14 and then 13. Right? And the last one, 3 digits have been chosen there. So this is the answer to the number of hexadecimal strings of length 4 with no duplicates in them. And notice it's just this principle in disguise. At each step, my alphabet size is changing in a predictable manner, but it's just changing in a very concrete way. 16 options, then 15, then 14, then 13 options. Okay. So I want to riff on this, and I know many of you in the audience and on the chat are familiar with what factorials are. I'm intentionally holding those out for a moment, so we will not answer those using factorials. It will be very difficult not to, for me as well, but I have a reason for what I'm doing here. All right, so let's jump ahead. let's answer some hexadecimal string problems. These are relatively straightforward, but they lead to some interesting things. Same type of questions as before, okay? So if we're now, instead of length 4, say I want a hex string of length 10, right? And length 16, and then C is a trick question of length 17, and I don't want repeats. Well, how is A going to go, right? It's going to be the same as before. We're going to have 16 options for the first, 15 for the second, 14 for the third, and I don't want to write 10 positions out, and I also want to leave you guys with the trick question. What will be the value here when I terminate this procedure, right? 16 options, the alphabet drops by 1 at each step, and I want 10 positions here. What will that be there? Very easy to make a mistake here. Or actually, it's more fun if you tell me what it's not.
It's not one.
It's not, okay, it's not 1, good answer. What else is it not? I mean, this is just for fun, right? You probably know what it is exactly.
It's not 2.
It's not 2,
It's not 6.
it's not 6,
It's 7.
yeah, it's not 7 either, so yeah. It's not 4, it's like, this is a, oh, sorry, Jake had it, I'm sorry, Jake, yeah. It's, yes, I got confused. It's not 6, right? One always makes this off by 1 mistakes. I do it all the time. It's not 6. If I had a 6 here, there'd be 11 characters in this list here. It's, I'm like, it is 7, right? Oh God, I shouldn't have made this joke. I'm like all confused now. We can always easily check, but yes, 7, like, okay, the easiest thing to see is with 2 here, it's 1 less. With 3 here, it's 2 less. With 9 here, it's, what? With 10 here, it's 9 less. Okay. Joke failed completely. It didn't work. Yeah. No wonder people get this off by 1 thing confusing. Yeah.
Fix it in post.
Fix it in post, yes. Yes. Okay, so it's that product. One can write it out. Did I do it here, the actual quantity? Probably not. Yeah, it's not too interesting necessarily what it is. You know, we could be pedantic, and maybe this first time it's worth doing. 14, 13, 12, 11, 10, 9, 8, 7. There's 10 numbers on that list there, okay? In a moment, I'll introduce a notation so you'll never have to worry about how many belong there. You just do a little simple computation, okay? Okay, what if we wanted hex strings of length 16? Then it's going to be 16 things here, and they're just going to keep dropping. What are you going to end with here? You go all the way down to 1, right? Like there's 16 positions and you have 16 characters. You have no choice but 16, 15, 14, 13, all the way down to 1. So let me erase this. 5, 4, 3, 2. And the final character, just like in the sumo wrestling example, there's only 1 option, right? You don't have any choice. Whatever character is left over goes there. Okay? So there's 16 of these. And now I see this very valid point in the chat. It'd be really nice if we had factorials here, but we'll get there in a moment. Okay? All right, now the trick question. What if I wanted a hex string of length 17 with no repeats? Yeah, you're shaking your head, right? You can't do it, right? There's like, forget about this model here. If you have 17 characters written down out of an alphabet of 16, you're going to get a repeat, okay? No matter what. I see Van making a face. I'm spoiling something that many of you are familiar with. Van's going to talk to us at length about a problem, this type of problem, okay? This is just a little warm-up for what we'll see later. Much later. I don't know, 5 hours from now maybe, something like that?
Time will tell.
Yes, time will tell, indeed. Okay. So that's that last one is 0. C is 0, right? That's not possible to do. And you might ask why, and I hope you see why, but if you don't, just wait. Okay. All right. So here's some problems without strings, but that are of the same type of doing this general product principle, and we're avoiding repeats. Okay. And so what the model will be here is we have 8 sprinters running the 100-meter dash, and I'm interested in different configurations they can attain in this race. Okay. So I'm going to do several versions here. Okay. I'll switch the camera here. And I'll label them so we can talk about what we're doing here. Okay. So problem A is we have 8 runners and they sprint. And let's suppose that we're ordering them on the track that has 8 lanes to begin with, right? There are 8 lanes and 8 people, and I'm going to assign to each lane one of the 8 people, okay? No person goes into 2 lanes. So let's start from inside lane 1. How many options do we have for placing a person there? there's 8, right? 8 people. In lane 1 can go any one of the 8 people. In lane 2, everyone can go but the person that's already been assigned to a lane. So there's 7 options for the second person. And then 6 for the third lane, 5 for the 4th lane, 4 for the 5th lane, 3 for the 6th lane, 2 for the 7th lane, 2 people are left at the end, times 1 person for the final lane there, okay? We could have also answered this person by person instead of lane by lane, right? This was lane 1 has 8 people, lane 2 has 7 people, lane 3 has 6 people. But we could have also said, oh, just go through the people ordered by age, say, and the oldest person has 8 lanes that they can choose. They can choose any of the 8 lanes, and then the second oldest person can choose any of the 7 remaining lanes. The third can choose any of the 6 remaining lanes, and so on and so forth. It's going to be either of those approaches you can take to solve this. Okay? So this is 8 lanes. Okay. What if we had 10 lanes instead? Right? Now the distinction between whether people are being assigned to lanes or lanes are being assigned to people becomes a little more acute. Right? Because if you go lane by lane, well, in the first lane, how many options are there for the first lane? Well, that's lane, so say lanes are choosing people to be assigned to them, right? How many different ways can I assign a person to lane 10, or lane 1, if there are 10 lanes? It's a trick question.
8.
8, but what if it's empty, right? It could be empty, right? And okay, you say, well, what about, okay, then 9, right? Empty is an option. How many times can I assign a lane an empty person, though? Only twice here, right? There's a possibility that, 2 lanes will be empty, but I can't have 3 empty lanes. So taking that approach is a little trickier. Instead, let's assign people to select a lane, right? So each person has a choice, okay? So person 1, person 1, person 2, all the way down to person 8, person 3, oops, person 3. Each of them has a choice. And again, well, the people are distinguished. We can rank them however we want. We don't even need to rank them. But then if they're selecting lanes, how many choices does person 1 have? 10, exactly. And there's no question here about what about empty lanes. That'll resolve itself at the end automatically. Once I've assigned 8 people, 2 lanes will be empty, the 2 that were never selected. Then person 2 has 9 lane choices. They can't go in the same lane as person 1. Person 8, all the way down to, should be 3 there, as we discussed a moment ago. Okay? Check this here. Okay? So it's this product here if we have 10 lanes. How do these two numbers compare? The second's, of course, larger, right? Notice this is 8, 7, 6, 5, 4, 3, 2, 1. This is 10, 9, 8, 7, 6, 5, down to 3. I've replaced a 2 and a 1 here with a 9 and a 10. Of course, this product's bigger, but it should be. There are more ways to put 8 people in 10 lanes than there are to put 8 people in 8 lanes. More options. Okay? What I did want you to notice, though, was figuring out who is getting what sometimes matters. In this problem, it didn't matter. We could go lanes to people, people to lanes. Here, you can solve it the other way. It's just harder. And so we can do it directly here. Okay. What about B now? This is a lovely, again, one of our sort of pretending tricks we've talked about a number of times here. So now we have 8 sprinters, and we're going to place them into 8 lanes. But we have this restriction that 2 of the sprinters, cat and row, have to be next to each other, right? What do we call this in elementary school? That you come in a combo or a pair or something?
Buddy system?
Buddy, yeah, I don't know. There's something, right? What's that?
Package deal?
Package deal, something like that, right? They have to be next to each other, otherwise they're not running. We're not going to have a race, okay? All right, well, how do we approach this problem? On the one hand, we could say, well, there's 8 times 7 times 6 times 4, 3, 2, 1 ways to put them all down in the lanes, but some of those are bad, right? Maybe in the 8 lanes, cat is here and row is here, and it's like, well, that wasn't good. We have to throw that out. But when row was here and cat was here, it was like, oh, that's good. That was good. And those two are together. So we have to figure out some trick for enumerating this. And here's the trick. I'm going to pretend that cat and row are just one person. That I have 7 people, and they're joined at the hip. They're just one person, and when they get put down, if cat is put in lane 7, row goes in lane 8 or in lane 6, right? They go together no matter what. Okay? So then I'm just pretending I have 7 people, and those 7 people get assigned to how many lanes then? it's a little confusing, but it'll just be to 7 lanes now, essentially. Like, one of the lanes will essentially be squeezed together in this metaphorical setup here, okay? Maybe we don't even have to weigh in on that exactly. So, let's look here. I'm solving B now. Okay, so now let's just imagine we're assigning these 7 people, one of which is a duplicate, into 7 lanes, okay? And then we'll figure it out there. So the lane that cat row gets assigned to is like a double wide lane. How many different ways can I assign them in this model? Well, the first person to choose has 7 options. Say cat row goes first, maybe that's the easiest. They have 7 different places they can be placed in, right? Notice they do not have 8 positions they can be put in. If they take up 2 together, they can take up 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6, 7, or 7, 8. There's only 7 options for them. So let's place them first, okay? So this is options for cat plus row together, okay? Once they've both been placed together, how many rows have been absorbed? The 2 people, 2 rows have been taken up. So now I'm on to the next person. There's 6 people left, and there's, 2 of the 8 rows have been taken. There's 6 people left, and there's 6 rows left. But now the problem's easy, right? We have 6 rows left and 6 people to assign to them. We just solved this in the previous problem, right? How many ways can we do this? Well, there's 6 options, 5, 4, 3, 2, 1. These are the number of options for remaining 6 people to 6 rows. Okay? That's a problem we've solved in part A with 8 people and 8 rows. Okay? So the wrinkle here was we pretended for a moment that cat and row were a single person and were assigned to 2. This is not the solution though. Right? There's a wrinkle here. Anybody see the wrinkle? Yeah, cat and row could be in row 1 and 2, but cat could be in 1 and row could be in 2, or row could be in 1 and cat could be in 2. Right? And that corresponds no matter where I put the 2 of them together. If they take these 2 rows together, they could be like this or like this. And there's independent of the other people's placings, these duplicate the total number of options, okay? So that's what I sort of like have to deal with. If I pretend they're one person, I have to keep in mind that, well, they aren't actually one person, and flipping them does change the situation. And so there's an extra 2 out front, okay? And this is just standard product principle. Here was the number of ways to assign the 7 people, right, to the 7 rows, and then this was the number of ways to fix our pretend here into assigning them to different places. And so you get this many ways of assigning them. This trick of merging people together into a pseudo person or a pseudo number, sometimes we'll see, is really powerful and really cool way of attacking a problem B that on the face of it looks tough, right? Again, there were 8, 7, 6, 5, 4, 3, 2, 1 ways to assign them in the first place, but we have to throw away a bunch of them when cat and row aren't together, and we don't want to solve it that way. That's very hard. I mean, you could write them down, but you don't want to do that. Okay, and then for part C, now we have the 8 sprinters, and they finish the race, and they get first, second, and third, right? Gold, silver, and bronze. And I'm totally uninterested in places 4 up to 8, right? If you don't podium, you didn't even run. No, I just made that up, I don't know. So, I used to be a runner, I made very few podiums, so anyway. So how many ways can we do this? Well, now the lanes aren't what matters, it's the actual positions in the race, and how many of our sprinters could take home gold? Any one of the 8, right? So any one of the 8 could take home gold. After gold's assigned, how many options are there for silver? Any of the remaining 7, yeah. And then the bronze, there's 6 options after that. I don't have any further things to multiply because in this problem at least, I'm only interested in the way the podium looks. The other placings don't affect this. There is a wrinkle here, and I've tried to solve this problem with this before, but it's tough. In reality, are these the only types of podiums? You guys know, follow the Olympics? There are other outcomes possible. It's rare. You can tie, and there's a few different ways of happening, right? In principle, you could have a 3-way tie, or even more, in fact. You can also have ties for second and so on, and so the podiums can look different. I'll leave that maybe as a nice homework for you. It is solvable. There is only some number of ways, but it gets challenging quickly. I think we'll need to see at least Ryan's talk to get the tools. I mean, it's doable without those, but his tools will definitely help us solve this. Okay. Okay, so I can continue with the sports analogies. I can't help myself. So, and I promise I'll tell you what a factorial is soon. Okay, so I hope everyone watched the World Cup recently. I was going to say this summer, but it was a different one. We're not that summer yet either. So say we have 11 players on the field, right? And we're about to take penalties at the end of the game. Right? And you select your 5 players to kick penalties from the 11 that are on the field. In fact, you often see late-minute substitutions precisely to allow this situation to happen. The other thing you need to know, and it's articulated here, is that the players that take the penalty kicks there's an order in which they take the kicks, right? There's a first, second, third, fourth, and fifth. Okay? So I want to know, out of my 11 players, how can I select 5 of them in order to take penalties, right? No different from the problems we've been solving. How many ways can I choose the first penalty kicker out of these 11? There's 11 choices, right? So 11 for the first, and then 10 for the second. We're just using our generalized product principle, our generalized string principle here. 9 for the third, 8 for the fourth, 7 for the fifth, okay? The reason I like to write this down is this is like 55,000 different combinations. So your poor manager has a lot of different options here in deciding how the penalty kicks will be taken. I mean, for an individual team, obviously you'll never come close to seeing all of these possibilities, okay? But it gets better. Let me show you the next example here. Very similar model.
Or you have a question?
Yes. The question in the
Question in the chat?
In the chat, oh. Does he mean football when he says soccer? Yes, I do. Did it say? Yeah, actually, I don't have any actual football examples, so yes, of course. In American football, there are no penalty kicks, to my knowledge. No, there are not. Yes, so I do. I do FlexiBear. Thank you for that. So I'll have to change the slides for next time. Okay, let's go here. All right, well, here I mean baseball and not cricket, definitely. All right, so in baseball, the way baseball works, you don't need to know the rules in order to solve this, but typically a roster has 13 position players. These are non-pitchers. These are the players that are eligible to bat, let's say, for the purpose of this exercise here. And the manager submits a lineup of 9 players. Say we're in the AL. AL uses DH, right? I haven't watched baseball in a while. Geez, I'm out of touch here. Van's got a baseball hat on. He can help me out, but yeah.
No, I think they did away with it.
They did away. I know.
They
It's all DH now. Yeah. Anyway, so I won't weigh in on that. My feelings about that, but yeah. Anyway, so you have 13 players available, and we're going to rank 9 of them to be the first person to bat, the second person to bat, third person to bat, and so on and so forth. Okay. So here for football, we had 11, 10, 9, 8, 7. There were 11 players, and we ranked 5 of them. Here, all we're doing is out of 13 players, we're going to rank 9 of them. So there'll be 13 options for the first, 12 for the second, 11 for the third, and down to the 9th. All right, our famously challenging problem here. What should be the final digit here? I'm asking for your help, literally. 5. 5. Thank you. Yes. Right. 4 would have been if there were 10 of them, and 5 is if there's 9 of them. So I take the product of these. Okay. This one I do want to know. There are. Oh no, I don't know if that's the answer to this question or the second question. I think that's the answer to the second. Okay. Would someone like to compute this for me real quick? I'm curious. But the follow-up question is, okay, this is the number of lineups you can make for an individual game. And you play 162 games in a season, so you do play a lot of games in a season. So in order to see all the possible lineups, how many seasons would I have to see? Well, this number over 162 games per season, right? In principle, in each game, I can see one of the different lineups. And I think this is like 1.6 million, right? So after 1.6 million years, could I see all of my possible lineups? I just think this stuff's great, right? Like this is such a simple everyday thing. Put 9 people in an order out of 13, like most of your team, and you'll just never even come close. In any tiniest fraction of all those lineups, you can never even come close to achieving, even in a season, right? Is 1.6 million right? I don't know if anyone checked. Yeah. Okay. Great. All right. Yes. Good. So.
How'd you do that in your head? How'd you know that was 1.6?
Yeah, I computed it last night, and yeah,
right.
I have it written down over here. Very good, Noah. Yeah, that would be a great question. Yes, if I had actually done that, there's probably some mental math trick, but no, not at all.
13 down
to 5 is 259,459,200.
259 million?
Yep, 459,200.
Okay, that'll be good enough, right?
Obviously.
Yeah, right.
Clearly.
But at least when you do see this quantity, you're like, oh, I divide by 162, then 2 million is like a reasonable thing, and yeah. So, okay, so now, that was the baseball rosters. Okay, finally, as promised, I will let us use the factorial notation so we can stop writing things of this type constantly, okay? So, what is a factorial? This is just a mathematical notation for shorthand for writing out descending products of this type. Okay? Everything's written there, but I'll highlight it on the board as well because this is very important and it's one of the coolest pieces of notation that there are. Okay? So, if I have a product that looks like n times n minus 1 times n minus 2 times n minus 3 and so on down to 3 times 2 times 1, like we've seen, or partial parts of this multiple times throughout. We've seen this guy occur. This can be written in shorthand as n exclamation mark. Okay? This thing means nothing other than just take the product of all of these guys together. Okay, so for instance, and we'll do a few on the next slide, 3 factorial is just 3 times 2 times 1, so it's 6, right? And 5 factorial is 5 times 4 times 3 times 2 times 1, which is that 120?
Yes.
It's good. I tend to try to have several of these memorized, but you know, it can be tough on the spot to remember. Okay, simple notation for this. One convention that we will use is that 0 factorial, well, it doesn't really fit in the model as defined here, right? Like, if I start from 0, like, I can't, 1 is above 0, I wouldn't go down to 1. So 0 factorial, like, according to this definition, is undefined for the moment. I will define it as 1, okay? Now, it's just notation, I can define it to be whatever I want. The reason I choose 1, we'll see later, there's notational situations where it's convenient to make it work this way. There are other good reasons too. 0 factorial can be thought of as the empty product, the product of no things. I'm not multiplying anything together. And there's also good reason, and we tend to define it this way, the empty product is defined to be 1 as well, for similar reasons, okay? But we'll use this convention. Sometimes this will be awkward, because occasionally you'll see things like something divided by 0 factorial, and you'll be like, wait a minute, you can't divide by 0. But 0 factorial is not 0, it's 1, okay? This isn't of extreme importance, but it will catch us occasionally, okay? And so again, this is pronounced n factorial, and it's a very wonderful shorthand for this thing here. Because I mean, I tend to like to avoid the dot dot dots if I can. This is totally unambiguous. Okay. It's also quite memorable, as we'll see in a moment. The exclamation mark is a really good metaphor for what's going on with this thing here. All right. So let's switch over here. And let's do a little bit of what I call factorial arithmetic, just to get ourselves comfortable using this notation here. Okay, so now I can erase this, although I guess it's going to come back soon. Okay, so what's n factorial? I'll rewrite that here. It's n minus 1, all the way down to 2, 1. Okay? And let's solve some simple problems here. Well, we already did 5 factorial in the previous slide. This is 120. What's 1 factorial? Well, it's not a very interesting case here, but we start with 1 and then just stop. There's just one term and it's just 1. 1 factorial is 1. 1 factorial is the same as 0 factorial. A little bit strange, but it's okay. And what about b? What happens when we divide factorials by each other? So 10 factorial over 7 factorial. This is a very convenient piece of notation. Let me write it out in full glory here. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, over 7, 6, 5, 4, 3, 2, 1. Those are the expressions, the 2 factorials there. What happens that's very nice here? We love it when this happens, right?
Cancellation.
A bunch of stuff cancels, exactly. So 7's, okay, now we're good. We're just left with 10 times 9 times 8, right? Which is really nice because, and we'll see this on a later slide, a multiple number of times we wanted to write out products like this, 10, 9, 8, 7, 6, 2, 1, or whatever. Now we can express it with the ratio of 2 factorials. this becomes very convenient. This is nicer to write sometimes than just these three. For 3, it's okay maybe to write it like that, but okay. What about, the green isn't so great, I'll continue with the black. What about 4 factorial over 0 factorial? Just as a reminder for what 0 factorial means. 0 factorial is just 1, so this is just 4 factorial over 1, which is just 4 factorial, which is just 4 times 3 times 2 times 1, which is just, what's that, 24? Yeah. Okay. So dividing by 0 factorial, like I promised, doesn't really do anything. And now let's simplify this one here. What if we're working with a factorial that's not just explicit numbers, but involves some variable, say n? Okay. So 3n plus 2 factorial over 3n minus 2. Okay. This one's a little bit harder to write out, but let's write out a few steps of this. So how do these products go? On the top, the first number in the product, maybe I should have used a different variable name here, but my n here is now 3n plus 2. Yeah, good. Let me switch this so you guys can see better. Yes. So 3n plus 2. What will be the next term in that product? What's the general rule for factorials? Yeah, it goes down. So it'll just be 1 less than this thing here. It'll be 3n plus 1. And then 3n. And then 3n minus 1. And then 3n minus 2. And so on, down to 2, 1. Okay? This one, obviously, you can't write out all the terms. N's not defined to be an explicit number here. But something nice did happen, because 3n minus 2 factorial drops down to 3n minus 3, 3n minus 4, and this goes all the way down to 2 and 1. And what happens in this situation? Same thing as before, right? We get a bunch of cancellation as well. So this cancels with this, cancels with this, cancels with, well, it's not written explicitly, but these cancel out with everything left here, and I'm only left with these 4 terms here. So when you write things like this, they're actually shorthand for just part of the factorial, right? It's a few terms, and if this is below this one, it'll just cancel out the remaining stuff. It can be very convenient to use this notation. Okay. One moment. Okay. Good. Okay. Yes, so now we have this nice theorem, which encapsulates all of this information, and lets us get a really nice shorthand for answering all the prior questions that we've done in this section. So there's our factorial. I'll leave that on the board. Now we have this theorem that says that the number, I mean, you can see it in the thing, but I'll rewrite this here, strings of length length k without repeat from alphabet of size n is, well, it claims to be n factorial over n minus k factorial, but the left-hand side of that expression is definitely the answer that we've seen using the product principle, right? What is it? Well, the first character in my length k string has n options for my alphabet. I can select anything for it, right? For the next one, I have n minus 1 options. I can't repeat what it has been previously repeated. Then n minus 2. And then, now Jake, I really need your help. It can be anyone, I'm just kidding. We've now gotten down to this situation. In k steps here, it will not be n minus k, but it'll be n minus k plus 1. Yeah, exactly, right? Easy to make this mistake. I always, every time I'm unsure, I go back to the first few and be like, the second term has a minus 1, the third term has a minus 2, so the kth term should have a minus k minus 1, say in parentheses, or minus k plus 1. Okay? I constantly forget it. But what is this in disguise? Well, if I looked at n factorial, it would be all of these, and then n minus k minus 1, n minus k minus 2, and so on. So if I divide this by n minus k, then all the terms that would have come after this are canceled with this guy here, okay? And what I like about this form is that it doesn't have this dot, dot, dot. It's just, that's the answer in this thing here. And this is easier to plug into your calculator. To plug this into your calculator, you need to say 12 times 11 times 10 times 9 times down to 4, or whatever. Here you can just say, give me n factorial, give me n minus k factorial, and just write out what the answer is from those two, okay? So this is the number of strings, but it also is our generalized product principle in disguise as well, right? If I'm assigning people to lanes, sprinters again, it's this option as well. Like the podiums was 8 options for the gold, 7 options for silver, 6 options for bronze, okay? But I could use this format instead. It would be 8 factorial divided by n, 8 minus 3 factorial. Okay? I'll do a couple of those real quick that we've already seen, I think. Okay. Yes, so I want to re-answer. Oh no, this is not the same as the hexadecimal ones. We're going to do decimal strings of certain lengths without repeated characters, and we're going to use this formula. We're no longer going to just say this times this times this times this times this. We're going to use the formula. Okay? All right, so in fact, I'm going to erase this part intentionally. Okay? I only want to use the formula directly. Good. So let's switch over the cameras, and I want to know how many decimal strings of length 10 without repeated characters are there. Well, we actually don't even need this model for that, but let's use it anyway. Okay, so A says length 10. And decimal strings, what's our alphabet size when we're talking about decimal strings? It's also 10, yes, good. So in A, according to this theorem, it should be 10 factorial divided by n and k are both 10. So 10 minus 10 factorial, which is 10 factorial over 0 factorial, which as we saw is just 10 factorial. Okay? Right? 0 factorial is 1. So there's 10 factorial ways to arrange a string of length 10 without repeats from 10 characters. Okay? What about length 6 without repeats? Well, here, now, n is still 10. There are n letters in my alphabet here. 10 letters in my alphabet. But k is length 6, so they're only length 6 now. So to answer this, I just say, oh, it's 10 factorial over 10 minus 6 factorial. Okay, so this is 10 factorial over 4 factorial. And that's typically how I would leave this answer here. But let's express it so that we can just sort of double check, sanity check, that is this giving us what we should get? So this can be written as 10, 9, 8, 7, 6, 5. Why did I stop at 5? Because 4 factorial would be 4, 3, 2, 1, which would cancel with the remaining 4, 3, 2, 1 in this one. So my answer would be this. I could plug that into a calculator, but let's look at that for a second and see if that would be the answer if we use the old rule, the old general product principle. Well, in that model, it would be, how many options do we have for the first digit? 10, any one of the 0 up to 9 characters. How many options do we have for the second character? 9, because you can't repeat whatever you used here. Then you have 8, because you've lost 2. Then 7, you've lost 3. Then 6, you've lost 4. And then 5, you've lost 5, and you're done here because now I've expressed 6 characters. Okay? So, yeah, I mean, I just proved it in 2 different ways here, but this is a good way to confirm our work here. Okay? All right, and then the silly one here. But let's see if it at least fits our model here. If I want a decimal string of length 1 without any repeated characters, there are 10 ways to do that. You choose 0 or 9, write it down, that's your whole string. Let's at least confirm that our theorem here gives us the right answer on that sort of edge case. Okay? Well, this would say 10 factorial, that always goes on top, right? My alphabet has 10 characters. Length k, so k is 1 here. So on the bottom would be 10 minus 1 factorial. So 10 factorial over 9 factorial. Well, there's going to be an awful lot of cancellation here. The 9 in this cancels with the 9 in this, the 8 in this cancels with the 8 in this. Let me just write it one more time. 10, 9, 8, 7, 6, 5, 4, 3, 2, oh no. 9, 8, 7, 6, 5, 4, 3, 2, 1. Yeah, this all cancels. And I'm just left with the 10 there. In this case, it's definitely good to simplify this down to the simple 10. In this case, I might leave this as 10 factorial over 4 factorial, or this is small enough to ask your calculator what it is, right? It's a reasonable number. Okay? So that's how you can answer those questions with this factorial notation. Okay. All right, back to Twister. We started the class off with Twister. We're going to talk about Twister one more time here. Okay, so we're going to have to make a few basic assumptions here to make this one work. But what I'm interested in is we have two players playing Twister, and I want to know how many ways can they be placed on this mat here after spinning the spinner, okay? Now you have to remember the rules of Twister. I'll just tell you simply that no circle can be shared by either person's hand or feet. Each can only be used by one body part at a time, okay? How many circles are there? Anybody remember? We answered this sometime an hour and a half ago. But there are 24, right? And that was early product principle 4 times 6. In fact, we can answer it in a new way. Instead of rows times columns, we can now do rows times colors. It's a little bit different model of solving this problem. Okay, there's 24, okay? All right, so let's suppose, you know, this Twister board is arranged in the room so that these circles are considered distinguished from one another, right? Because there is a certain symmetry here. Those of you mathematicians are very familiar with what I mean here. Let's pretend there's no, you know, symmetries here, just to make the problem more solvable. Okay? So how would we figure this one out? And I want to solve it using our new rule. Okay? So with two players, you have 4 hands and feet for each, and these are distinguished from each other. My hand and left hand and Ryan's right foot are not the same body part, right? Yes, good. It's okay. So if my left hand is on the first red, and whatever else happens, or there's a different arrangement where Ryan's right foot is on the first red, those will be different no matter what. These are different. We're two different people, and our hands and feet are different from one another's as well. So there are 8 body parts to be placed on this board here, and there are 24 unique positions. We've decided that they're unique positions. So isn't this just a string problem in disguise, right? We're building up a string of length what? Well, let's arrange the body parts in order. My left hand first, then right hand, then left foot, then right foot, and then Ryan's in the same order come next, okay? There's 8 in that order. How many options would I have for my first body part? It can go to any of the 24. And then for the second, there's 23 available, because I can't put it the same. So I could answer it 24 times 23 times 22 times 21, going down 8 steps. Or I can use this approach here and be like, well, the length, I got something wrong here. What did I get wrong? Help. It's length 8. But, what? But it can't be, oh, look, yes, length 8, yes. Sorry, thanks, Anna, yes. I was seeing reverse numbers. One thing you never want to see, for now, I do not want this result to be a negative number. I do not know what negative factorials are as of this moment, and this would never make sense anyway, because you would never have a string of length k without a repeat from an alphabet of size less than k, right? We already saw that earlier on with 17 out of 16. Okay. But here, our word is of length 8, right? The word is which, you know, which circle each of those 8 body parts get. So it'll be 8 factorial. What? No. I'm insisting on doing it wrong here. Yes. The alphabet is of size 24. There are 24 positions that are assigned to the 8 body parts. Yes. I'm thinking too much like Twister, where I assign a body part to a circle, but it's better to think in the reverse. I assign a circle to a body part, and actually that's how the game works. You spin the spinner and it tells you where you have to go. Yes. So my alphabet in this case is 24 factorial, and the number of, the value of the denominator here is 24 minus 8 factorial. So we get 24 factorial over 16 factorial, which I didn't compute, but that's already a big number. There's a lot of different Twister games that can be played with 2 players. Some of them presumably are infeasible. I wish I had a board here, but like you probably can't do the bottom left arm on red and the bottom and the other hand on the up right. It's like you have to be really tall to fit across it. I guess, I don't know. I haven't played Twister since I was in high school probably, so anyhow. Okay. Where, oh, I don't want to be there. Yes, okay, so, what are we doing on time? Oh, great. We've talked about strings a bunch so far. Strings are a very fundamental object in counting and in discrete math. And I want to talk about another one, permutations, which we will see a lot about a few hours from now as well. But I want to do a few problems with permutations. They're very closely related and counted by factorial functions, okay? So what is a permutation, without going into too much detail? It's just a collection, you have a collection of objects and you just rank them in some order. Okay, and we've been doing these already a bunch now, right? If I take 8 sprinters and put them in order of the places that they finished the race, that's a permutation of those 8 sprinters. Or I could take everyone in this room and arrange us in a line in many, many different ways. Each of those lines is a permutation of the individuals, okay? So the objects are shuffled, essentially, into a different order, okay? And there are many ways of doing this. That's indeed, it says, in other words, this is just a string where every object appears once. So let's look at some examples here. Let's look at permutations of, say, 3 objects. Okay? Let's say we have, well, let's just take the numbers, no, let's take letters. Let's take the letters A, B, and C. Okay? These could be 3 numbers, they could be 3 people, they could be 3 buildings on campus, it can be 3 chairs, anything you like. And a permutation of these objects is just a listing of them in order. Okay? So we'll be interested in how many permutations there are, but before we do that, tell me a permutation of these objects.
ABC.
ABC, the boring one, right? But a very important one. The one where they kind of kept the original order in which I described them. Just ABC, that's a particular ranking of ABC. What's another one? BAC, that was the one I was thinking of too. Okay, what else?
Cab.
Cab, good. Yeah, this is actually fun because you get some words. Cab, what else? There's more than this. CBA also has a meaning. Right? Actually, these are fun, right? Okay, ABC means something, right, the ABCs. BAC is blood alcohol concentration, means something. CAB is a word. CBA, collective bargaining agreement. All right, what else?
BCA.
BCA. Almost. There's BCAAs, which are branched chain amino acids, but that's just BCA. So, I don't know, is BCA anything? Yeah, anyway. I mean, anyway. What else? How many we have?
Permutation of ABC.
Is it, Van, did you say it's a permutation of ABC? Yes, good answer. And
ACB.
ACB, we don't have that? ACB? ACBC? 1, 2, 3, 4, 5, 6. There are 6 of them only, but why? We're going to figure that out in a moment here, okay? So we listed 6 of them here. What if I was looking at permutations of, say, 1, 2, 3, 1, 2, 3? Would the situation be any different? I mean, not really. There'd still be the same amount of these, right? In fact, why? Why would there be 6 of these and 6 of these at the same time? Can someone explain why?
The first place you have three things, the second place you have 2 things, the third place you have 1 thing.
Okay, so Noah, you're actually proving the amount through that argument, which is great. And I'll get to that in the next slide, actually. So you're a step ahead, which is fantastic. What I'm looking for here is why would there be as many in this list as there were in this list? Yes, what you said is an answer. I want another way of viewing it.
3 distinct things.
Yeah, they're like, I have 3 objects, 1, 2, 3, and 3 objects, ABC. I could pretend A is 1, B is 2, C is 3. And like this list would also give me that list, right? What's important isn't the things in the list so much as the quantity of them, right? If this were 1, 2, 7, it wouldn't matter. Or AB 4, it wouldn't matter. It's just that I had a number of distinct objects, okay? So that's really all that matters, is the size of the alphabet, which we've seen a number of times as well, right? The size of the alphabet is what determines how many things, not the actual contents of it, okay? All right. What if instead, though, what if I had 1, 2, 3, 4? How many permutations? Okay, I don't want you to answer that. Compared to this, how many permutations would you guess?
More.
More, thank you. That's the answer I wanted. There should be more. There's more things to shuffle up. There's more ways to shuffle it up. In fact, if you think for a little bit here, if I shuffle all these up and then just throw away the 3 from all of them, just discard that, I'll have a bunch of shufflings of 1, 2, 4 included in that list. But there's a bunch, the 3 can be moved around within this. Okay. Anyhow. Okay, so let's jump ahead and answer the question you guys have already been answering. Is There are n factorial ways to permute n objects, okay? Right? And, okay, I'll write a proof of this. This is our first proof format here, okay? So how many ways can I make a permutation of n objects? Well, what is a permutation? It's a string of length equal to the number of things we have in our alphabet, right? Okay, so we have several ways of solving that. One version was, we had a theorem that was erased here that said, hey, if you have length k word from an alphabet of size n, the answer is n factorial divided by n minus k factorial. Right? So I'll just say via prior theorem. This is a bad practice maybe in here because we don't remember the theorem, but it should be we have n length string without repeats from alphabet of size n, right? This is a very particular instance of that theorem, okay? And there you can see. This was answered by the theorem that said it was n factorial over n minus k, but my k here is n minus n factorial. So this is again n factorial over 0 factorial. And I told you 0 factorial is 1, so this is just n factorial. Okay, QED, right? That's a proof of the theorem, using this other theorem. But let's not prove it this way. This is not the way it's typically proved. Typically I would prove it in the following way, just using the product principle. And let's look at this example here. Proof by example, which is not really a proof, but still can be handy for understanding what's going on. Suppose n is 4, and I want to know how many things am I going to see in the list of these guys here. Okay? And Noah said it to us exactly. It's a word of length 4, where all 4 of these characters appear with no repeats. Right? So there are 4 options for the first character in my string, and then 3 options for the second character in my string. I can't repeat. Then 2 for the third, because I can't repeat what was used here, times 1. At the end, I have no choices, right? I've exhausted all but the last one. So 4 times 3 times 2 times 1, which equals 4 factorial. And I hope you'll believe me that this proof had nothing to do with 4, right? If there were 10 objects, it would have been 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. If there was 100 objects, it would be 100 factorial. Okay? So that's another way of seeing this argument without using the prior theorem, but using the product principle. Okay, so I want to say a few words about permutations, about permutations and this number n factorial, because it is awesome. Okay, so take a deck of cards with 52 cards in it, okay? Shuffle it up. What have you created when you shuffle the cards? You created a permutation of those cards. You rank them from top to bottom, you put them in order, and there's no repeats, obviously. Each card appears once and only once in the deck. Shuffle it, shuffle it, shuffle it. There's 52 factorial ways to make a shuffling, right? Every different way of putting those cards in order is an outcome from a shuffle, and there are 52 cards, so 52 factorial. It's just a permutation, okay? This number is hilarious, okay? It's so big, that's how big it is, written out, right? 52 factorial, I don't actually, did I compute this? Yeah, that has 67 digits in it there. It can just fit on there. I even had to change the font size to get it to fit. So 67 digits long. That's what it looks like.
How many trailing zeros does it have?
Yes, Van asks how many trailing zeros are there. I think he's going to teach us that, right? Yes, I think later we will discover, like you notice there's a bunch of zeros at the end, and it seems like a bit of an oddity. Why would there be a bunch of zeros there? And why are there that many? There is a way to figure that out, but that will come in a few hours from now. That's a really cool problem. Okay? Yeah. So that's 52 factorial. Even more amusing, I plug this into Wolfram Alpha, and that's it in words, apparently. So I'm not going to read that out to you, but apparently the first 2 digits are in the unvingingtillionth place. I didn't even know that was a thing. But there, in words, that is actually the description of the word. Notice it ends at 824 trillion, and then that's it, because again, you have all those zeros at the end. So there's no millions, billions, thousands, hundreds, and so on. Okay? I want to say a couple words about this number, because the fact that this number is so big is important. you may have heard this term, we call it combinatorial explosion sometimes, and this is the idea that counting problems, permutations, but all the like, they get immense very, very quickly, right? This quantity, 52 factorial, is huge, but the object you're working with is very mundane, right? A deck of cards, like everyone has a deck of cards, you've shuffled it before, it's like no big deal. It's just a simple object, it's not that complicated. And yet, with those 52 distinguished objects, you can describe a number that's so big that maybe I'll write a few things on the board here. So there are some interesting comparisons to make, right? Anytime you see a number this big, people always say, oh, number of atoms in the universe, number of this, number of that. I want to say that stuff because it's interesting. So 52 factorial.
Cory, please. Cory?
Yes? Oh, okay, thanks. Yeah, oh yeah, like you literally can't see anything now on the stream, right? Okay, good. So 52 factorial is about 8 times 10 to the 67. Oh yeah, so 68 digits. Okay? It's about that large, right? I mean, you can see it expressed explicitly there. I was curious, and I asked Wolfram Alpha, how old is the universe in seconds? Right? It should be big, right? It's like 13 billion years old, so, you figure out seconds, it's not that hard to figure out. But the universe, so age of universe in seconds is what? I almost had this memorized because it was so funny. So 4.3 times 10 to the 17th. Right, that's an 18-digit long number of seconds old the universe is. That number is so puny compared to that one, like it's nothing. In fact, what this tells us, for instance, is imagine you were shuffling a deck many, many times per second. It would take you something like 10 to the 50th shuffles per second to see every single different shuffle in the length of the time the universe has been around, right? Like just divide this number by this number to see how many different individual shuffles would I have to have occur at an individual point in time, second, in order to see all of these shuffles eventually, right? They're all different. I'm curious how long would it take to see all of them. I went further actually. Seconds are not the smallest unit of measure in time. Anybody know what that is? Any physicists in there? Yeah, there's a Planck second or Planck second, right? It's like I don't know enough physics to tell you guys anything about it, but it's the minimal, inseparable amount of time that there is. It can be described, it's the amount of time it takes light to cover maybe one Planck length. That's got to be it, right? Which is the smallest distance. So you can actually ask instead the age of the universe in Planck time units. I don't know what they're called. Planck seconds? I don't know, I'm sure there's a word for it. I looked that up, and there are 8.1 times 10 to the 60th of those. Okay, there's a lot of those. But still, even if you do one shuffle per Planck time for the length of the universe time, you will still come up 7 zeros short of the total number of shuffles of the deck of 52 cards. And I think this is astonishing that all these enormous numbers in terms of what's going on in our universe pale in comparison to a humble deck of cards, what they can give you with a simple description. We won't compute it, but there's another consequence of this. That there's so many of these that what it means, in all of human history and all of the times we've ever shuffled a deck of cards, if we shuffle it correctly, not just poorly, that you've never had the same deck of cards in your hand ever as some other person. There's so many of them, if you shuffle truly randomly. Now this is in reality not true, right? When you buy a deck of cards, it's shuffled and they're probably in the same fixed order. But were you to truly shuffle them, you would never get the same shuffling twice. No matter how hard you tried. There's just too many of them for it to have any likelihood of success. Which again, I think is amazing, right? So what it means is no person's ever played the same game of poker. It's impossible because the deck, you'll just never have the same deck. That's wild, right? It's just this tiny little thing. Okay, all right, so now we know factorials are big. Let's compute a couple factorial problems, and then we're coming up on what I'll call the capstone for this section, where we'll do one particularly interesting problem. Okay? All right, so let's get a little more comfortable with factorials and solve a couple relatively elementary problems with them. Okay? All right, so the first is just how many permutations are there of the numbers 1 through 9? Right? We have a theorem for this. How many ways can I shuffle up 9 numbers? We don't need to even think anymore. 9 things, shuffle them all up. There's 9 factorial ways to do it. Right? That's simple enough. Okay, what if I want to shuffle up 1 through 9 1 through 9, but I want 1, 2, 3 to occur together? Okay? So the permutation 1, 3, 5, 2, 6, 4, whatever isn't valid because 1, 2, 3 don't contain glued together. How do I solve this? We've seen this trick before. You guys remember which problem was similar to this?
Cat and row?
Yes, the cat and row sprinters, where we pretended the sprinter was one person if they had to be together. This is the same thing. We're just going to pretend that 1, 2, 3 is its own number, right? Just pretend it's some special number. 1, 2, 3. I don't know. Like it's a number, then, right? It's a symbol. Right? I don't know. So if that's its own symbol, how many now words or letters do we have to work with in this permutation?
7.
Is it 7? Yeah, I can't do the arithmetic. We have 1, 2, 3, and then 4, 5, 6, 7, 8, 9, 7. Okay, 7. So the answer should be 7 factorial, right? Because what happens when we permute these, we get, here's one permutation, right? It's 4, 7, 2, oh, not that. 6, 1, 2, 3, 5, 8, 9. Did I get them all?
Yeah.
Yeah. These were forced to be together because I pretended they were one thing. Okay, that's again one of our pretend mathematical tricks we've been repeating over and over and over again. Okay, so I basically lost 2 letters because the 2 and 3 got merged into the 1. That's another option too. I could just say, oh, throw away 2 and 3, permute 1, 4, 5, 6, 7, 8, 9, and then after I've done that, squeeze 2, 3 in after. Okay? Yeah, remember the string has to be 1, 2, 3 in order. 2, 1, 3 isn't valid here. Okay? Although we can actually tweak this problem in a nice way too. What if I wanted to know the number of permutations where 1, 2, 3 were next to each other? Maybe not in order 1, 2, 3, but I could have, but it would be valid if it was like 4, 7, 6, 3, 2, 1, 5, 8, 9. Okay? Then thinking of 1, 2, 3 as its own number is a little tricky because there's like a 3, 2, 1 is another option as well. You guys see how we might solve that? We just need to riff on this, right? I see some thumbs ups. So the trick here would be first, still think of 1, 2, 3 as its own special number. Let's call it pi. Pi will represent 1, 2, 3. Finally, I mean, geez, we're 2.5 hours in, I haven't said the word pi yet. It's sort of like kind of, anyway. So we'll pretend that this is pi. Okay. Shift everything up in 7 factorial ways, right? Once we've done that and shifted in 7 factorial ways, the 1, 2, 3 now needs to be addressed. It could appear 1, 2, 3, but it could appear 3, 2, 1, or 2, 1, 3, or blah, 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 or blah, blah, blah. How many ways can I fix this thing once I've found its position? 3 factorial. It has 3 factorial ways that it can be arranged inside in the second step. Okay? So that's the answer. You can just multiply those 2 quantities. That's not the question that's articulated on the board there. Maybe let me put, this is b prime. 7 factorial times 3 factorial. Okay. How about C? This is a nice one. Say we have 50,000 people and they go into a football stadium. I mean, association football. And they fill a stadium completely. There's 50,000 seats, 50,000 people. How many different ways can I seat them in the stadium? All of the seats are unique. All the people are unique. Just yell it out. What's the answer?
50,000 factorial.
Yes, exactly. 50,000 factorial. How big do you think that is?
Bigger than 52 factorial.
Yes, 52 factorial was already hilariously large. I actually don't know. If someone cares to plug it into Wolfram, surely it'll tell us how many zeros it has. I think it's worth seeing. I think Wolfram can do it. There are algorithms for figuring out how many digits. It probably will not attempt to write out the full string, although that would be really funny.
Do you want the power of 10?
Yes.
Yeah, so it's just 3.34 times 10 to the 213,236.
Okay. I was a little worried it would be a 10 to something. It won't take long, right? So this has over 200,000 digits in it, right? I mean, forget even comparing to this like atoms in the universe. Like it's just a waste. Like you'll just divide it and have 213 2 35, or like, okay, not that, but like a few digits lower, and like it's still too big to even wrap your head around, so, yeah. Okay, and then, oh yeah, there was one more question here. And that is, okay, this one's a bit like this B prime. This is a nice problem here. Let me describe this one to you here. Okay, so we have 9 people, and they're gonna sit in a row together, okay? But we have this rule that there are a specific group of 5 that all sit in the leftmost 5 seats. And then the remaining 4 people all sit in the remaining 4 seats, okay? So we have a group of friends that are like, no, we have to sit together. I don't care what the rest of you 4 do, okay? So if there were no stipulations whatsoever, how could we seat the 9 people in those 9 seats? Just 9 factorial, exactly, right? So 9 factorial, we just shuffle them up. That's just a shuffling problem. But now in this problem, it doesn't work that way. Now we have 5 specific people that are going to be assigned to these 5 seats, and then the remaining 4 are going to be assigned to these 4 seats. Right? But actually, it's not that hard in disguise either, because we can just do this problem in 2 steps. Right? The 5 people are maybe the 5 of us here. We have to sit together. How many ways can we assign us to these specific 5 seats? Just 5 factorial. Forget about the other people. They'll deal with it afterwards. So there's 5 factorial ways to, seat the 5 sort of obnoxious people. And then of the remaining 4, they can be seated in the remaining 4 seats however they want in 4 factorial ways. So that's the product there. There's a follow-up question that I can't answer for you guys yet, but Ryan can. I don't know if he will necessarily, but what if instead I just said that, hey, I want those 5 people to sit together, but I don't care that they're in the first 5. They could be in the first 5, the second 5, the third 5, the fourth 5, fifth, or which, however many groups of 5. That's a little bit harder. We do have the tools maybe in principle to address it, but Ryan will equip us with more stuff to answer that question. Okay. All right, so what are we doing here? 20? Okay, I think it's going to be perfect here. So let me answer one more question and then do the capstone here, okay? All right, so let's say we have a group of n cats and n dogs, and we want to arrange them in alternating fashion. Dog, cat, dog, cat, dog, cat, or cat, dog, cat, dog, cat, dog. And good luck, right? This is like, my dad they have 2 new puppies, right? He's been trying to send me photos of the 2 puppies like together, and like, just send video, right? Photos, it's blurry, like you can never get them to sit still, so anyway, so this is a truly imaginary, this is just as bad a problem as like the, John's going to the store to buy 80 watermelons, right? This is just as unrealistic as that. So, okay. So how do we solve this? This is similar to the seating the people in the seats in the previous one, but it has a bit of a wrinkle to it. Okay. Well, we're going to alternate cat, dog, cat, dog, cat, dog. But let's just ignore the cats for a moment. The dogs come in some order, right? Independent of where the cats appear. How many ways can I just put the dogs in order before I even introduce the cats to the equation? Yeah, exactly. So let's say the dogs are here. Dogs in n factorial ways. Okay? And then let's get the cats. I don't know, what do you think is harder, to get n dogs to sit still in a row or n cats to sit still in a row?
And cats.
And cats, yeah. They don't do what you want, right? Like, how many ways can we shuffle the cats? Also n factorial, doesn't matter. Again, to emphasize again, the objects aren't what matter, it's how many of them. Okay, so cats in n factorial ways as well. Okay, so that's the number of ways to shuffle them. Now, I'm not done with the problem because I need to interlace them with each other. However, most of this is done for me, right? The first dog and the first cat should be next to each other. The second dog and the second cat should be next to each other. So I'm sort of told what I have to do. So it seems at first glance that it should be, whatever the number of ways to arrange the dogs is, times whatever the number of ways to arrange the cats is. Notice this is product principle in disguise. But I'm missing one thing that a problem allows for that I didn't specify. Yeah?
So with a cat or a dog?
Yeah, exactly, right? Whether I interlace them like this or like this matters, right? First cat or first dog. But there's only 2 options there. As soon as I said cat is first, then it means cat, dog, and so on. And if I say dog first, then it's dog, cat, dog, cat. So there's just an additional 2. So the answer is 2 times n factorial times n factorial. If you like, this is 2 times n factorial squared. You can do that if you like. Okay. All right, so now let's jump over to the birthday paradox, which many of you have heard of, I'm sure. I want to explain what's going on here, okay? So the idea behind the birthday paradox is the following, and we'll do some problems to motivate and make it make sense. But the idea is that if you have a relatively small group of people, in this case 23, we'll see, there's a relatively high probability 2 people will have the same birthday, which seems a little counterintuitive, right? There's 365 birthdays. Doesn't it feel like it's very likely we're just distributed if we have 23 people and don't have a repeated birthday, right? That's why it's called a paradox. I looked this up on Wikipedia last night. It's a paradox of a very special type because it's not actually a paradox. Like it's paradoxical, but there's no paradox. It's like we will compute and you will see that the answer is what it is and it works out perfectly. So paradox is kind of a misnomer, I guess. But I mean, that's not really that important. Okay. So let's try and solve this here, and I'll ask a warm-up question here, because this is one of the reasons it makes it difficult. Okay, so we are going to work with 365 potential birthdays, okay? Sorry, those of you that have leap year birthdays. You don't count in this problem, okay? Yeah, although we could make it 366 and the problem wouldn't change too much, okay? So the first question, and this isn't really my section to be answering this is Van's, but I'll still ask it here, because I like to give a little hints for later, is how do we know for certain no questions asked that we'll have 2 people on the same day, with the same day birthday? Like no matter what, 100% probability.
366.
Yeah, 366, right? Yeah, Keith, if we had 365, we might just, that seems unlikely that we'd not have a repeat, but it's possible everyone has each day of the year a different birthday. But once you get 366, there's no way to distribute them and avoid a collision, we might call it. Okay, so this is 366, which is nice, but this isn't really what we're talking about. It's not really a counting type problem in the sense I've been talking about. Okay? Okay. But that guarantees it 100%. But now what I want to focus on is, suppose we have 23 people, even before that. Let's figure out the number of ways to have 2 people with different birthdays from each other, okay? And let's notice that this is just a counting problem of the type we've been doing here. It's just a string problem, right? Say we have 2 people. How many birthdays could I potentially have in our model here?
365.
Yeah, 365, right? With first person, so person 1's birthday. And I'm interested in I don't know where I got that number from. Yeah, I'm approaching 3 hours in, so I'm getting a little, 365. There's 365 birthdays available for person 1. For person 2, if they must have a different birthday from me, there's 364 birthdays available. Right? Jeez, wow, 364. This is person 2, right? Notice this is exactly the type of problems we've been doing, where the number you have one less choice for the previous than after assigning the first. So there's this, whatever this product is, that's the number of ways for 2 people to have 2 different birthdays in the year. I could be January 1st, you could be December 25th, or I could be January 12th, and you could be February 7th, or like, whatever. There's tons of options. Okay? So this is 2 people. What about for 3 people? Same thing, right? It's 365 times 364 times 363. But actually, I'd like to use our theorem we had a while ago, where we have divide factorials by each other. So what am I creating here? I'm creating a string, right, of distinct birthdays listed in a row. The length of this string will be the number of people I'm talking about. So the length of this was 2, right? The length of this was 3. Okay? So according to that other theorem, we have a length 3 string with no repeats from an alphabet of size what? What's our alphabet in this problem here?
Days.
The valid days for birthdays, right? The 365 valid days. Okay, so according to that theorem, there should be 365 factorial divided by 365 minus the length, in this case 3, right? Factorial. And this, of course, is just 365, 364, 363, right? Because this will be 362 factorial, which will cancel off all the other terms from that. So I'll just be left with those 3 in front, okay? And that works up here as well. But this notation is much more convenient to work with in this problem than I don't want to write down 365, 364, 363, 23 times. Even with the dot, 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 I don't want to do it. Okay? So then for the final part of this problem, what if we have 23 people? Well, I smell coffee and it smells amazing. No, I'm kidding. No, I'm kidding. So with 23 people, there's 365 is our alphabet size. And then it's going to be length 23. I want them to be different birthdays from each other. Okay, I got to at least get a sip of water. All right. What will go on the bottom here then? We're looking at the case where we're talking about 23 people, which seems to be pulled out of thin air. At the end, we'll see why I pulled that out of thin air. So it should be 365 minus 23.
342.
Yeah, is that what it is? I can't, oh boy. Okay, minus 23 factorial. So 365 over 342 factorial, indeed, okay? That's not easy to compute by hand, right? Because it's 365, 364, there's 23 terms in it. But you can plug that into a calculator or Wolfram and get something. I don't need to know it just yet, okay? Now, that's the conclusion of part B, is this is the question I'm most interested in. Let me circle it. I know green's not too visible, but at least for like, that's really bad. Oh yeah, this was the decent one. So I'm gonna keep this one around. This is handy. Okay, so what is this actually answering? Number of ways 23 people can have different birthdays. Right? Remember we agreed that's the thing we computed. 365, 364, and so on. Okay, now I want to answer the question of how many ways can 23 people simply have birthdays with no restrictions whatsoever? That's again a product principle problem we've done before. Okay, so the other thing I want to know is number of ways 23 people can have birthdays, let's just say without restriction. Right? Because this is the reality, or at least some partial reality. You can have your birthday whenever, right? Like anything's possible. Birthdays do have a certain distribution. They're not evenly distributed. We're going to pretend that they are for this problem. It turns out, it's very interesting, that in reality that birthdays are not evenly distributed actually makes this more likely to happen, not less likely to happen. Okay? But I don't want to get into that. That's relatively advanced probability theory. Okay, how many ways can I assign birthdays to 23 people if I allow for repeats?
365 to the 23.
Yeah, 365 to the power 23, right? Each person has 365 options, no restrictions whatsoever. Okay, now we haven't done any probability to this point, but I hope this one at least is reasonable for us. This is the total number of ways 23 people could have birthdays, just period. That's all the different ways they can have. They could all be January 1st, or they can have 23 different ones, or who knows what. This is all the ways in which 23 people can have different birthdays from each other. So using these two, I can figure out this, the probability that 23 people have distinct birthdays. Okay? This is just a counting problem in disguise. This is the total number of ways for 23 people to have different ones. This is the total number of ways to have them, period. What's the probability then of this event? You just divide them. Yes, exactly. It's just 365 factorial divided by 342 factorial divided by, okay, maybe, I don't know what the nicest way to draw this is, divided by 365 to the 23. Okay. It's the result of this thing here. That's the probability that 23 people have distinct birthdays. This is the number of ways to have distinct birthdays. This is the number of ways to have birthdays, period. This is everything that can happen in the universe. These are the ones that we're interested in. Actually, we're not quite interested in that. We're interested in the opposite of that, but that's fine. We'll look at this. Okay, this you don't want to do by hand, but you can use a calculator for it, or Wolfram. Let's look at it for a second, though, just to think about what's going on here. How many terms are in the product in the denominator? 23, right? It's raised to that power. How many terms are in the product in the numerator? It's less obvious, but it's also 23, right? It's less easy to read out of this, but there are 23 left over after you cancel things out from each other. And that makes sense too, because remember how we assigned them. First person had that many options, second person had that many options. You took 23 steps. Okay, so before we do any computations, let's think about what's up here. So this is 365 23 times. The top decomposes into, what's the first term in that product? 365. Okay, well that'd cancel with one of these 365s, so let's not worry about that. What's the second term in this result here? 364. That's a little bit smaller than 367. Woo! It's a little bit smaller than 365. Then the next one's 363, which is even a little bit smaller, right? So there's like the ratios are getting smaller and smaller and smaller. What certainly can we say about this product here?
Smaller than 1.
That's important, right? I mean, it is a probability. It better be smaller than 1. But like you just have a bunch of fractions times each other, each of which is smaller than 1. So they get smaller and smaller, but they're pretty close to 1. Even when you get down to the 343 over 365, like that's still big-ish. But there's enough products that it gets small. In fact, it is less than, I wrote it down here, 4927. Right? That can be checked. I say right as if you guys could like see that it's that. If you use your calculator, you will find that it's less. It turns out to be less than that. Okay. If I kept adding terms to it, like had 27 people, and this dropped 27 terms, this would continue to get smaller and smaller and smaller and smaller. There'd be more terms in the product that are less than 1 being multiplied by each other. Something we learn early on when we get our first calculator, that when you multiply things by numbers less than 1, the product mysteriously gets smaller, not bigger. That's always, I think, a revelation for people with mathematics. That happens here. What does this mean, though? This is the probability 23 people have distinct birthdays. That probability is less than 49. It's less than 49%. Well, okay, it's less than 50%, let's say, it's safer. Right? Yes, it's actually more than 40%, 49%. So what does that mean for the probability that 2 people do have the same birthday? What's the relationship between 2 people having the same birthday out of 23 versus 23 not having the same birthday? The complementary events, right? One happens or the other happens. They're just opposites of each other. So what this means is that the probability that of 23 people to have the same birthday, this quantity will be greater than, it'll be 1 minus this number here. The point is it's greater than 50%. I'll write it in this fashion here, okay? So there's about a 50-50 chance in a classroom of 23 people that 2 people have the same birthday, which I think is remarkable, right? Like why should it be that? Okay, all right. So there's a follow-up question to this, and there's also, I want to talk a little bit about the paradox here, because, okay, I did this computation, fine, the answer was 50%, but you don't really have like a feeling for like, well, first of all, where did 23 come from? That was because if I plug in different values of this I can affect this probability, and we'll do that in a moment. But before I even do that, I want to talk about another way of estimating this that maybe is a little bit more illuminating, but it's an estimate, it's not exact, okay? So let's see if I can remember how to do this. Let's think for a second here, because this is the key thing in this problem. So I told this to my 14-year-old yesterday, and he said, well, wait a minute, I don't think there's anyone in my school that has the same birthday as me. And there's like in 8th grade, there's a few hundred 8th graders, right? And it's like, well, not too many, like, yeah. Well, actually, even that wouldn't matter. There's a few hundred 8th graders, he doesn't think someone has the same birthday. And it's like, well, wait a minute, shouldn't that be incredibly unlikely? Notice what this doesn't say. This doesn't say that I am likely to have a shared birthday with someone, right? It rather says that there's some 2 people among those 23 that will have the same birthday as one another, okay? So I want to ask the following question just for a second. For just any particular 2 people, what's the probability they have different birthdays? Okay? Just 2 people. We actually answered this a moment ago, right? So if you look at 2 individual people, the probability they have a different birthday, is 365 times 364. That's the total number of ways to have two distinct birthdays. And what are the total number of ways the two of them could have birthdays? 365 squared, right? I'll write 365 for me, 365 for you, right? This is the probability me and Van have different birthdays. Okay? We don't have the same birthday, by it just so happens, but the probability is this thing here. And notice these two cancel out, so we get this really nice 364 over 365. That's close to 1, right? It's 99% chance me and Van have different birthdays, right? If the birthdays are distributed even. That's very likely, right? I fix a day, Van has almost all the days to safely choose a birthday and be different. So it's very likely we have different birthdays. But here's where things get interesting. Okay, fine, me and Van had different birthdays. But what about me and Anna? That's another computation. What's the probability me and Anna have the same birthday? Or different birthdays, let's say. It's the same thing. It's 364 over 365, right? There's a little bit here. If you know that Van and I have different birthdays, it affects the probability that Anna and I have different birthdays. But I want to throw that out for now. I'm just trying to estimate, right? So me and Van having the same birthday is a different birthday is 99% or about 1% chance that we have the same. Me and Anna, probability is about 1% that we have the same. But I get to do that pairing with every single person. Anna gets to do that pairing with every person. Ryan gets to do it with every person. There's a bunch of potential pairs. In fact, how many different things do we have to examine that might potentially have the same birthday as each other?
Number of people choose to.
Don't say that. Those are Ryan's words.
Number of people, times number of people minus 1, divided by 2.
Yes, good. Yes. All we need to do is figure out how many ways to pick two people, right? Out of 23. So number of pairs. Yeah. Do we have a special thing for that? The number of pairs of people from 23. Well, in a few moments, Ryan's going to come up here and tell you a really sweet way to compute such things. But let's just do this. Number of ways to pick two people out of 23. Well, person 1 can be picked in 23 ways. Person 2 can be picked in 22 ways, right? But we should divide by 2. You could pick me then Anna, or Anna then me. That's the same pairing, so we divide by 2. This is actually a very nice product principle example in disguise. Okay, this is this is 253. I think it was.
Yes.
Awesome. So this is crucial. There are 253 opportunities for two people to have the same birthday, right? This is why you only need 23 people. It's not the number of people, but it's the number of pairs of people that matter, okay? This is not accurate, but in order for there to be no repeated birthday, this thing needs to occur 253 times. Not exactly this thing, these events are not independent. I don't want to get into probability theory. But if you raise this thing to the 253, March Madness is like upon us, and this is a very nice example here. Exponents are very strong. If you have a very high chance of something, but you raise it to a power, it goes away very, very quickly. A famous example is literally March Madness. If you could predict each match in March Madness with 99% accuracy, you still would not fill out a perfect bracket. Like, your chances would still be minuscule, even if you had 99% chance in each round of doing it. This is even worse. You have 99% chance of having a different birthday, but you need to accomplish that 253 times. This is multiplied out, gets you, I think it comes out to be, it's like 0.499, okay? It's an estimate, it's not accurate, because again, these events are not independent, without saying more. Okay, all right, so let me wrap it up then, if Ryan doesn't mind me going over a few minutes here. With the following question. What if I want a 99% probability that two people have the same birthday? Okay, so now I want to work it from the other way. Before I said with 23 people, we get about a 50-50. Here I have a target now. I want 99% chance. I want to see how to solve this. I've erased them, but we have most of the tools on the board here. Okay? So I would like to know what will give a 99% chance of having two people with the same birthday. We know what will give a 100% chance, right? We saw that already. We need 366 people to get a 100% chance, right? Yeah. To get 50% chance, we needed 23. What do we need to get 99, right? And you can change 99 to 99.9 if you want, or whatever. We'll do 99% chance. Okay, so how do we do that? Well, let's say K is the number of people. So K is number of people needed for 99% chance 2 with same birthday. Okay. So I don't know what k is, I'm trying to figure out k in this problem. Okay, so we're going to be looking at a probability, and let's compute instead the probability that everyone has a different birthday and show that that has less than 1% chance of happening, right? If everyone has if there's a 1% chance of all k people having a different birthday, then there's a 99% chance that 2 people actually did have the same birthday. How many different ways can I assign birthdays to k people with no restrictions? 365 raised to the k. Right? Remember our old problem, k was 23. K is now, I don't know what k is. Okay, what about the number of ways to assign k birthdays to people so that we have no repeat? Well, that's going to be some sort of factorial over factorial, right? It's a length k string chosen from an alphabet of size 365 without repeats. So it's 365 factorial over 365 minus k factorial, right? That was an earlier theorem we used. So this quantity here, okay? This is the probability, okay, let me write that. This is the probability no 2 of k have same birthday. In other words, this is the probability all k have distinct birthdays. It's another way of putting it. It equals this. What would I desire this to be in order to answer my question? I want 2 to have the same birthday, so I want this to be unlikely. I want 2 people, all k people having distinct birthdays, I want that to be unlikely. Right? So I want this to go down below 0.01. If there's a less than 1% chance of this happening, there's a 99% chance of the opposite happening. Okay, this is just the same as the previous problem with the k here, and I was looking for 50-50, not 0, or not 0-1. Okay? How do I solve this? It's a trick question.
Try different Ks.
Yeah, okay, actually, that's good. That's what I would do. You could plot this, you could ask Wolfram, you could just plug in values of k. Like, okay, without even knowing it, maybe some of you guys know, what do you think k might be? In fact, I want to record these because it's fun. Anyone, give me a value of k you might think, we'll see. Ryan, I'm literally going to ask everyone for a number, so.
24.
24?
Let's do, I don't know, 152. Why not?
Yeah, sure. I mean, there's no good intuition here, so. Well, there's some tricks, but Van?
151.
Oh, that's, okay, I'm not going to put names, actually, because, okay, 151. Linda?
The green's not really showing.
You wanna give it?
130.
130, okay. Noah?
Green's not really
Oh, Noah's left. Keith?
Let's do 62.
62. Russell, yeah.
68.
68? Okay. Anna?
89.
89, okay. I forgot. It's 59. Yeah, 59, which is kind of cool. Right? It's actually 59. But you guys see that, like, okay, solving for k was basically impossible because k is up in the exponent here and it's in part of this factorial, like solving for it. But you can just plot this, or like, I think you can like type this into Wolfram, or Anna's suggestion is like, you plug in 152, say, and you're going to see this is like 0.000001. You're like, okay, let's try 62, and then actually that's really close. Who was 62? Was that you, Keith? That was you, Keith. Nice guess. Had you seen this before?
I've done some work for this.
I see. Okay, sweet. All right. Okay, good. So that, I think, can I spoil the next funny slide?
Please.
Okay. I mean, it's you, Ryan, I think, but,
Yeah.
so we'll take a couple minutes break here. But I think, yes, let me turn off that will be the introduction to the next section. So thanks very much, everybody. I will see you like 9 hours from now, if I'm still on my feet, but yeah. Okay, great. So we'll pause the stream for a few minutes here. I mean, it'll still be up, but I'm gonna mute and we'll switch some things around. Ryan will join you in a minute.